Hello, humans. Is there anyone to tell me that if the video is working?
Daniel, if there's any way you can up the font size on that window a bit, I think that will make some of your attendees have an easier time reading it.
So you mean I should increase the font size?
That would be my suggestion, yeah, on that terminal window. I mean, the slides are fine. The terminal window was pretty small.
Oh, let me see if I have time to do that. I will try to crop the video. Thanks for the suggestion. Yeah, no, cropping the video won't work now. I already did on a lower resolution. Like it was on full HD instead of me going in 4K. Yeah, it might be too small.
Hello, Daniel. Are you here, Daniel?
Yep, yep.
Oh,
I can hear you, Andrea.
okay. And do you hear me well?
Yes, perfectly. Do you want to try your slides?
Sure.
Okay, there's a problem. You
Okay.
have an echo. And now your audio is coming twice.
Oh.
And my voice is really bad.
That's strange. I don't hear the echo.
Don't you?
No, he sounds good here.
Do you think
I
you have
hear-
double big blue on your side, something like that?
My bad. I opened the YouTube.
Live stream. The live stream?
Yes.
Okay. Yeah.
Yes, as far as I opened it to share on Twitter, and the audio was coming through the two interface. Okay, my bad. It's not a problem. Do you want to try your slides?
Yeah. Do you have I uploaded on
Yeah.
the website? Okay.
Yeah. I've set you as a presenter, and if you go with the plus sign in the bottom
Sure.
left,
Oh, cool.
you can click on it, and there is an option. I think it's manage slides. Yeah. Yeah. Andrezão.
Cool. And can you see me now?
Loading. Yes, here you are.
Awesome.
Nice,
Cool.
Mustard.
Thank you. Yeah, few texts, la. Rich interface, backup slides. Yeah, since that my webcam is working, the mic is good, right?
Yeah.
Slides are good. Okay. So I think I'm good. Good to go. Cool.
Thank you, Mother.
Sure. And how about the chat? Is Matrix working today?
We hope so.
Okay.
Sebastian, do you want to try the interface as a speaker?
Yeah, sure.
Okay, good. We have tested because it seems that your microphone is a little bit low.
Is this any better?
Yes. So
Und
I will.
louder?
It's perfect now.
Okay.
So I made you the presenter. I will probably switch to your slides before your presentation starts. But in case I missed it, you can do yourself too. And it's easy. You just need to go to the plus sign in the bottom left of the screen and manage presentations. Yeah,
Like
very
that,
good.
right?
Yes, perfect.
Awesome.
Is there anyone else that would like to try the system? Anyone of the
Yes.
presenters? Davo, John Kaser, Yuri, anyone else? If you guys would like to help me on taking notes, all the help is welcome. I will not ask Daniel Wagner because I know he doesn't like it.
Sorry, what do you need there?
We need to take notes during the micro conference. There is a shared notes tab in the top
Okay.
of the top left. If you could help with just take notes of the things that are happening. Because
I can do my best. I'm not always the best note taker, but I'll help out.
no, any help, if you see that that there are discussions going on and nothing is being written in the notes, jump and write something there because we will be
Okay.
asking. Stephen will ask us these notes. And it's always good to keep Stephen happy.
And you all set? Ready to go?
No, I'm still preparing my coffee, but once it's done, we are
Which
ready.
I have to get mine. I'm behind because I was all set up outside and the wind started picking up and I realized that I can't speak with the wind going because everyone else. When I turn my mic on, all you hear is a big whoosh. So I had to move everything inside, which delayed.
Yeah.
I'll be
But-
hanging out
but-
in this conference.
Yeah, but everything is fine. I already uploaded the slide, tried some presenters, and yeah, we should be good to go. I asked the people to take notes because you will ask us about the notes.
Yep. Maybe I'll even try to take some notes for you.
Yeah, thanks.
Steve, we are relying on you to take the notes now.
Well, just remember, because I'm on the program committee, if there are any issues or anything come up, I may be pulled off. So I may not. Yeah, I'll take notes, but I may not be a reliable source. That's how I get out of taking notes. Be on program committees.
The only true statement maybe was, I am not reliable.
But you keep inviting me to do the work.
Because we like you.
I never said you were intelligent.
Let's get started. Hello, humans, and welcome to the real-time micro conference at the Linux Plumbers 2021. So, before start, we would like to say thanks, really thanks for the Linux Plumbers conference sponsors. We have Facebook as Diamond sponsor. We have IBM as Platinum sponsor. We have ARM and Microsoft as Gold sponsors. And Amazon AWS, Netflix, and Red Hat as Silver sponsors. We also would like to say thanks for Collabora for the speaker's gift sponsor, and VMware for the t-shirts. Also, Linux Foundation with the conference services. Always good to count on them. And so, before I start, it's important to clarify that, yes, this is a micro conference. Yes, there will be a lot of discussions here. But let's try to keep a friendly environment, an inviting environment. We will see talks here from people that are old figures in the community. We have talks from newcomers. Let's receive everybody very well and let's be kind. Nevertheless, there will be discussions. As long as they are technical, it's good. Let's keep it as technical as possible. If you feel uncomfortable, please reach us, right? So, in order to keep the system running well, this is a big conference, please keep your microphone and cameras muted when not participating on the discussions. So, if you want to make a comment or ask a question, turn your camera on and wait the people ask you to talk, to express yourself, right? And after you finish your topic, please turn the camera on and let's keep the environment running smoothly. So we would like to thank the LPC 2021 Planning Committee. It is a tough work having the organization. I'm working on the RTMC and the scheduler microconference. It's already a lot of work, and for the entire conference, it's even more work. So thanks, David Woodhouse, Elena Zanoni, Kate Stewart, James Bothling, Christian Browner, Jonathan Corbett, and Guy Leonard, and our beloved Stephen Roston. No, we are not in a break. So, not yet. So we'll start with our first topic from Sebastian. Sebastian, are you ready?
I'm ready, yes.
So I think we can start now. And final request. We need to take notes of the discussions here because it will be used later, right? For the people that could not attend and would like to read what we're discussing here. So please join us, take notes. I will do my best on taking notes, but I'm not a native speaker. You guys will see a lot of typos. It's just more work fixing them. So if you write well and would like help, please join us in this effort. And yes, Sebastian, it's all yours now.
I made Sebastian presenter, so you should have control,
Okay.
Sebastian.
Okay, hello everyone. I'm maintaining the frame.t queue. My name is Sebastian Sieger, and I will try to share how we maintaining the queue right now and what we intend to change or what might change when we hit upstream completely. So right now we're handling everything in a single quilt queue. Using Git never worked out due to the workflow we usually have to follow. So basically what we do is on each new version, stable or completely new upstream release, we take the queue and we push it up patch by patch until it applies completely. And then we try to make sure it compiles, it works. And during the process, we try to address new issues that show up or react to reports based on the mailing list. And for every new release we make out there, we started around 3.8, 3.6, something in that area, to import the complete queue into Git, since people ask for it. So we did it. And we don't keep the patches around forever. We try to fix, to fold back fixes into the original patch if this is the case. Like we have like one patch fixing an issue and then we have to adjust it again. Then we retest from time to time the patches to see if the original issue that we had some time back still applies. And depending on the patch that it handles, we either submit it directly upstream, and sometimes we rework the infrastructure more or less. Prominent example is, for instance, the software queue handling. While in the 3.2 area, we started with one threaded interrupt per software queue per CPU. And in the end, we ended up with something very, very close to what mainline is doing right now. So we basically got also the same problems, but the duct tape we had around software queue to make it work disappeared by a large number. Another example is log, for instance. In the early days, we had recursive locking here, and it even worked cross CPU. But the thing that reached mainline doesn't do either of that. It's only, it cannot nest right now, and that's what's intended. And this is basically the based on lessons learned what we had in the RTQ, which acted more or less like a staging tree. So we could test drive the code and see how it works. And in the end, we were able to submit a solution that was something that we like in the end. And then we use and go upstream tree by tree and try to land the patches there. So sometimes it's like one tree for a specific feature. Sometimes it's 10 trees or even more, depending on how invasive it is. Now, I have no idea how the future workflow will be due to the unforeseen things in the future. But the obvious things are that the changes have to end up in the upstream tree of the relevant maintainer right away. And one thing I actually hope for is that since RT is mainline, then testing could also be done before the code of the other maintainers or contributors hits upstream. Because right now we usually see that something broke once we update RT to the relevant kernel version and then try to fix the issue at hand. A few things I saw in the recent months is that people try to avoid warnings that came up with RT or RT relevant code. So I hope in the long term that this doesn't happen like all the time and people try to understand what's going on and don't try just to work around the warning and keep working as is. Another thing I hope that comes with the future is that people don't assume things that RT might want and might not want in terms of latency, in terms of code structures, like making a raw spin log every time there is a warning or so, and just try and talk to the RT developers first before making any radical decisions. One example is, for instance, the commit I mentioned below is just one example I just came up with making the slides. The thing is that with thread interrupts, and a warning came up, and people independently started to fix it, like patch and device by device. And then the GPO maintainer actually came around and saw that it's actually the same pattern for each and every device. And then he came around and asked the IRQ maintainers if this is the right approach. And then Thomas looked at it and was like, well, not necessarily. We could fix it in their core infrastructure right away. And at that time, it was actually one fix that fixed several problems. The commit message has actually all the details, because we had also other issues in the NAPI interface versus the H timer, which we're sitting on for years, and we didn't know really how to tackle it. But this one change actually made a difference. Now, this is actually everything from my side so far, and I'm actually open for discussion right now.
So let's start with a question. When the merge happens, right? The regular, let's say, non-RT developers will start to have to deal with the restrictions that we have, like, for example, usage of logs and all those things. How do you plan to address these kind of situations, right? How can they know who to contact, or how can we catch these problems earlier?
Yeah, I guess my question, Sebastian, was going to be, do we consider RT to be a subsystem? Therefore, should we have entries in the maintainers file? And because that's going to be the only way for people to say, who do I talk to? You know, I mean, I know to talk to you or Thomas or somebody like that, but somebody who's new to the community is going to be, huh? How do I get in contact with somebody? Because this RT kernel is freaking out on me.
Well, it's the RT kernel. It's easy to go for the RT maintainers. Logdep has like the one warning for nested logs which are exposed to non-RT to RT problems. So that will be like one way to go. But other than that, it's actually always specific to the subsystem in place that may need to interact with the RT part as well.
So
I guess I was just, go ahead, Stephen.
yeah, I was just saying, one thing we might want to, also Thomas has raised his hand as well, but Mike, one thing I want to ask or suggest is maybe we should need a way that if there's an error, like a locked up splat that's, you know, due to, you know, the preempt RT locking order, we really need to have a way that really expresses who to talk to, because a driver writer gets this locked up splat, they won't understand it. They're like, wait, I don't understand. Why can't I grab this spin lock with this other spin lock? What's the rationale between the two spin locks? They may not understand that. And we need a way that if they do get maintainers, or maybe, I don't know if there's a report, who to report to. I guess we need some sort of methodology to report something to say, if maybe we should imply that, if, you know, you've had this bug, here's the people you need to contact that you should talk to for this problem. Because I just got an email today from someone says, I got this lock, or I got this crash. Who do I talk to? And they have no idea. So I think we need some sort of methodology that if it's a real-time problem or a locked up splat, that we say, this locked up splat is due to real-time issues. Talk to these people to help you fix it, or email this mailing list. But we don't have anything like that right now, do we?
Just
No
the
notation.
just the Linux RT users list, but that's actually much more generic.
Thomas?
So maybe another point, even before that, I was thinking that we might
need more automated CI to actually test. I mean, ideally, all the patches that are meant for upstream to test them with the RT config option enabled, because I guess most of the developers will still not care about RT, and then maybe we don't. I mean, we realize we have a problem when it's already being merged potentially. So I was thinking, I was actually wondering, I think you might already have something along the line that does CI testing automatically, and probably we can help, or how do you actually think it's a good idea or something that is needed?
Yes, this is generally needed. From what I know, my devil tree is tested by the K robot with the preempt RT config enabled. And I hope that the other bots pick it up as well once it's completely mainline.
Right, yeah. So maybe, I'm not sure, I mean, one option would be to enhance even that further. I mean, we also test, I think the ARC guys test the RT releases basically on Fedora with the full RT on. So I think we just need to tell them to continue doing that after everything is merged by using the RT enabled.
Yes, this would definitely help.
This is a general problem. I mean, if you look at a lot of the Sysbot reports, they get an RCU stall, and you have no freaking clue why. I mean, this is often enough hard to identify where something comes from. But on the other hand, if you have run something with config preempt or T enabled, or one of the robots does that, and then it splats, and then the developer comes along and says, hey, but if I disable preempt or T, it's gone. I mean, it's pretty obvious whom to talk to. So I'm not too worried about that. I mean, this is, we have the same problem versus RCU and other non-obvious things which have very, very interesting limitations. I mean, the only thing we can do is actually add enough debug in order to make it obvious where stuff goes wrong, and then usually people find their way to talk to the right people, or ask somebody if it's either inside the company, ask a senior person, or ask some generic maintainer who might redirect them to the right place. So I don't think it's fundamentally different from what we have in general.
And
Thomas.
actually, I just real quick, I just want to say exactly, that was one of my point, is that this is not just a real preempt RT problem. This is RCU problem. This is other subsystem, or this is other problems with subsystems that affect the entire kernel, not just, you know, if a driver goes bad, you call that driver. If the scheduler is something off the scheduler, you go to the scheduler maintainers. If you have something like real-time or RCU that you get these weird errors, and you're like, why is this a problem, and not understand it, people actually don't even know it's an RCU problem sometimes. Or, okay, Splat, talk to RCU people. Maybe we need some, you know, infrastructure that makes it a little bit more obvious, or a reporting structure. Real-time has helped the Linux kernel in general so much throughout the years. Why is this any different? Why don't we create something that will make it easier to talk to the right people? Yeah, you could, if you know the right people, that's one thing. But if you don't know the right people, there'll be a lot of bugs that just go unreported.
That's my complaint, is that we're sitting here preaching to the choir. Everybody here knows everybody else for the most part. It's the people that are going to be coming in later that I worry about. Would it be worth creating a directory and documentation with just a couple of text files that say, if you encounter a problem running a preempt RT kernel, email this list?
That's not enough. You need something that's more like a get maintainer script. You need a script. We need to start pushing a script, writing a script that reads a bug report and says, here's the likely people to go talk to.
Yeah, but I mean, Steven, get maintainers is great, but I didn't even know about it until last week when you told me about it.
What about adding a line to the splat when preempt RT is enabled, saying please report these to the RT users mailing list.
We could have it so it's in the splat that we actually have a report. In the RCU, same thing. Have a command say report this to this mailing list, and
I
it
like
should be a
that.
mailing list, not a person.
Yeah,
One thing I also have to
I don't
remember
want
is
I don't want my email address in the. We could put GLX
if there's somebody you really don't like, you can add their address.
Yeah,
The
I'll submit that badge.
but remember, it doesn't. If preempt RT is not set, LockDep checks for locking errors without preempt RT being set. It will look for, if you call raw spin lock and then spin lock right underneath it. I believe Peter created a LockDep incident where you'll get a LockDep splat, and preempt RT is not anywhere to be defined.
This is correct, yes.
Yeah, you have to
Probably.
enable it, which triggers a lot of noise right now on the mainline on a non-RT enabled kernel. That's a problem we have to think about what we do about that in the long run. But coming back to the original problem, so you can do what you want. I mean, you look at LockDep splats. I've just saw today in the morning, I just ran into, I enabled RCU list debugging, proof RCU list, and I ran into 4-year-old code, which is still exposing the splats there because it's not annotating the call when it does it on the reader side, on the writer side, or just using a regular list operation there. So, I mean, people either ignore stuff or they work around it in the weirdest ways. That's a matter of fact. And no matter what you do, documentation won't help, and random entries talk to X won't help either.
I just know you were looking at me when you said work around things in the weirdest way.
Well, like I said, just because there's always going to be people like Clark that does the roundabout way, there are still people that that would fix it if they knew about it better. And I believe it's always a good idea to have a way of letting
When it
people know.
/star.
Yeah.
There's the tendency to make it work and run away. Work in parentheses.
Well, I actually don't see any of these being mutually exclusive.
No, I mean we can add more information. That's not a problem, but it won't prevent people from doing the wrong thing. That's
It's really more in the matter of, okay, you've done something crazy or you've tried something and it didn't work, and how do you go? What's the right way for you to go fix it?
right.
So this is something we should bring up at our stable RT meeting to say, okay, who's going to set out action items, who's going to write the documentation or fix the comments, or probably.
Yeah.
We need an action item on this, at least someplace to pass the buck to.
Well, let's go ahead and bring it up at the next stable RT, and we don't have to dump it all on one person because I know Stephen, who you're looking at. But I mean, we can share the load there, and it's actually not going to be a bunch of stuff that goes directly into stable RT. It's going to be submitting up to LK minimal.
It won't be for stable RT. It'll be actually focused towards upstream, but something that we could, as because real time's at mainline now, our stable RT meetings are going to have to switch gears a little bit. We're running out of work to do.
Oh, I don't see that happening.
One thing with regards to the CI, one suggestion would be for us to provide a list of tests that people could add to their CIs, because a lot of companies already have CIs in place. So if they run the tests that we care about, that will help us.
Right.
The other thing is the combination of options. I was just fiddling around trying to get, doing a config that wasn't a monster Fedora or a full up Debian config, and turned on a few debugging options that I had never turned on, and bada bing, bada boom, there were all kinds of splats and complaints that came out of that. So when we start talking about these CI jobs, it may be worth us pushing towards saying, okay, let's try as many of the oddball options as we possibly can. What is that, fuzzing? Or I forget what the term is for going through and trying all the combinations of config options. But we do need to, I think we do need to get more coverage in a lot of these areas, because we all have our own favorite set of configs we use, and we kind of get stuck in those, and maybe missing some valuable splats and information about failures we didn't know about by not stepping out and using a wider variety of debugging configs anyway.
Clark,
Yeah.
how many distros are you expecting to run preempt RT turned on by default?
Wow, I have no idea.
Because,
I mean, we have an offering. I don't. Is Oracle offering an RT kernel by default?
I don't know.
And
Debian does. Debian ships an
Debian
extra
does?
kernel with the RT kernel, actually. Yes.
Okay.
And
I don't know if Fedora will or not. We probably need to talk to them about it.
The reason I bring this up is if that config's not enabled, it's actually going to be very hard for you to try to get most of these companies to try preempt RT in their CI, because that's not part of their standard process.
Hey, I'll ask. If they don't want to do it, that's fine. We'll work with what we can.
Okay.
There's also the embedded crowd as well, who constitute an awful lot of drivers.
Yep.
And are like, some of them will definitely be interested in RT. Obviously, that's one of the big use cases.
You know, I gotta wonder if the only way we're going to get any kind of CI and coverage on something like that is through virtualization. Because trying to get the right kind of bare metal support for doing that could be just insane. But I agree with you that what everybody's generally calling edge computing these days, or maybe not everybody, but a lot of people are calling it edge, are going to constitute a good chunk of our use case for preempt RT.
Yeah, I mean, if we get anywhere with, I know Daniel was working on getting some basic RT testing into kernel CI. If we get anywhere with that, we can get a pretty good sense of how bad the situation is fairly quickly, because we can get stuff run on a fairly wide selection of boards without too much trouble, which we'll not be able to leave it running if it's too bad, but it'll at least give us a sense of what the situation looks like.
Yeah, so the situation there in the kernel CI or Lava testing, all pieces are now there. We basically just have to start running them on doing the normal builds or whatever that means. So currently I'm just using a local Python script which generates the jobs and triggers the build. But this is obviously not the integration you have on kernel CI. So ideally you have kernel CI builds which trigger the Lava build, Lava testing. I think this is the logical next step we have to do for that kind of testing.
Yeah, I agree, and then we can give it a run on, if we get it integrated, give it a run on kernel CI staging server, and then see how practical it is to actually deploy it at this point.
Yeah, I mean, there's, if I remember correctly, there's already the kind of prototype running for this, but I think we just have to roll it out for more configurations, for more boards. I think this is, yeah, we have to talk to those guys, yeah.
Yeah.
You know, Is your lava testing mainly functional testing, Daniel? Or are you
Oh,
trying to do any
well, now what thing I've done is basically I've enabled all the RT tests which are there, and have the scripts around and make the command line options, everything like streamlined. And now I started to play with workloads, so you can basically the main test is running cycle tests with different workloads, and one of those was just running for example stress ng. I was playing a bit with that one, and obviously you could have more workloads which might trigger something.
Yeah, biggest problem we've had with doing automated testing is at least on the server class boxes, you have to do a lot of BIOS tuning to make it perform properly, because those BIOSes tend to like to grab the system and not let go for a while. So it becomes difficult for you to automate any kind of testing that checks performance to say, oh, look, we've had a performance regression coming through. So most of our automated testing is functional, just because, you know, is yeah, did this work or didn't it? And we don't try and do the try and do some sort of performance check to say, have we changed over time?
Yeah, but even that would be a plus side if we do that, because when I run stress ng for the first time, like with all the tests, I run into one of the allocation errors done in the scheduling path, for example. So, I mean, that would be already a good thing forward, I guess, if we have this automated. So, if new code is added, that we have at least no regression in that part.
Yeah, and like with the embedded stuff, the firmware. I mean, you can get issues with firmwares, but they're less common at the minute.
Yeah. Also, the embedded devices usually tend to have more simple firmwares or no firmware, which allows you to get more consistent results. But my experience is if you have really to know your specific hardware box, what the capabilities are. If you change small things, you get different performance values. So not sure if that works out.
Yeah, I mean, that's what I was partly what I was saying about running it across the entire fleet of boards, you know, and getting a sense of what the results look like and whether it's set, you know, what the best way to look at enabling it is. If it's a case of going through board by board and trying to figure out if it works, or whether we can just turn it on and then there's a few boards that need some care and love to work.
Yeah. So one thing I've added to the testing environment is basically that you can upload the results from cycling tests for post-processing, something very simple. And I was playing with the idea to plot it in the long run. And basically what OSDL did or does already, but integrated into kernel CI Lava environment so that we can basically use larger fleets of test equipment.
But maybe some of these performance problems can be overcome by knowing the hardware that you're testing and knowing the expected results, right?
Yeah.
So if you say that, okay, on my board, it will not reach that 50 microseconds that I aim, because I know that this board has some hardware interference that I can measure using the tools like hardware not detector, right? So aware of that, the tool could first do a profiling of the system, set up the baseline, and see how the baseline varies over the time.
Yeah, exactly. That's the thing I'm doing. I have a couple of hardwares. I know exactly, basically, the expected results, and if something goes wrong in updating something, I know, okay, there's something strange happening right now. And you need to build this kind of confidence for each hardware platform, each box, basically. You can't really predict it for anything new.
Yeah, it's a per use case. And actually, as all this data is automatically generated, it would be important to have a way to automatically watch the result. So,
Yeah.
okay, and the algorithm will say, okay, I know that in the past the values were these. Now I saw a variation. Why it happened?
Yeah, I mean, if the good thing about embedded stuff usually is not that expensive compared to big server infrastructure. I mean, you could run a fleet of them, which gives you also a bit more input data. Because usually you have to run it more than like 5 minutes, right, to get any interesting results.
Sebastian, do you have comments, final thoughts in those last minutes? Things you would like to add?
No, I don't think so. I mean, in general, the fleet testing sounds like a good idea. Also broad testing in general. But also the part where you try to navigate the people to the right folks to talk to.
Comments, people? Yeah, we still have like 3 minutes. So anyone else has questions for Sebastian? Clark, you always have questions?
Why are you looking at me, man?
I don't know. you are good on using this part time.
I'm thinking we've pretty much solved all the real-time problems today just in this first session, so we should all go get a beer now.
No, there's my talk now.
Oh, that's true.
My
Right.
talk, otherwise.
You're next. Okay. All right.
But yes, it was a nice presentation. Thanks, Sebastian, and it was a good discussion. And it's nice to see this level of engagement of the community. That's what we expect on a micro conference.
Thank you.
Thank you. So, okay, I will slowly start my topic. It starts in the next 3 minutes. So, just connecting the things before I start to respect the schedule. So, people that might join the right time. These tools can be used in this to collect data from people that doesn't know what to trace or where to start when dealing with the problems with RT. Maybe like people that never used the RT that saw some bad numbers and would like to send a report of, okay, I saw this bad latency, that's where to start. But I'll discuss about this later. And there will be more topics about lava and water. Okay, I will start 2 minutes early. So, yeah, I guess people know me. I'm Daniel. I work for Red Hat. And the talk here is about the new tooling for testing the performance aspects of the perimeter RT. And the name of the tool is RTLA. It's not Los Angeles, it's Linux analysis, real-time Linux analysis. And before I start, I have to say that this is a sub-product of the topics I was presenting in last year's, like the RTSL that I presented last year. I got a proof of concept and took out some sub-products. It will return in the future, but these addresses the problems that we have nowadays. Right? On our daily work, RTSL will be in the future. So, yeah, let's start. It's the correct time now. So nowadays, we use a set of black box tools that mimics some kind of workload that we aim to use or to maximize the values on the parameter RT, right? So we have cyclic test for the case of periodic test that we try to mimic, and that's our more traditional tool, right? But something that we have been I would not say ignored, but not paying as much attention as it needed. It is the case of busy loop tasks. You know, we have a lot of customers, even before the story of network function virtualization. Many people on stock exchange, they use busy looping tasks, and they try to maximize the availability of the CPU for a single task, right? And then you have sysjitter, and then OSLET that came to fill the void that sysjitter was leaving. So generally, we run these tools and see the values, right? And but when some unexpected value happens, we need to put our hands in the third part of the work. And it generally involves setting up a traces session manually, right? And this is not easy, not always easy, let's say. When we have someone else operating the system for you, I've probably worked for years at Red Hat support, and many times I had to instruct the customer how to run the test, how to collect the trace, right? And that involves a lot of back and forth of communication. And it works, but it could be improved. And mostly it involves a lot of interpretation of data, right? Let's say computing deltas between two events that we always do over and over again. And when we don't have like a clear, let's say at least a starting point, a lot of speculation goes on. And speculation is misleading because let's see, in the next you understand why. So you never know when you run the test and you see a bad number, you never know if the problem you solve now is the same problem that you solve later. Let's say one common thing that I see is there's a problem that happens almost every year, right? Almost every month. Then you see a bad number and people start guessing out what happened. They do some change that has nothing to do with the original problem because you don't have an evidence of the regular problem. And then because the problem doesn't happen frequently, the speculation pointing to the misleading direction becomes a truth that it's not a truth. And that's especially hard. And that is especially hard when we start to have like very tight values, like when people are targeting tens of microseconds, right? But after all these years having to debug this kind of problems at Red Hat, you know, for the vast majority of people that's developing the RT, the starting point is almost a mechanical thing, right? And so any mechanical thing should be replaced by an automatic way to do things. So, and that is the root of the OS noise and timer law tracers. These tracers already landed in the kernel, right? And the idea here is that they are not only tracers, but they also dispatch a workload that is tied to the tracing. So, and in these two cases, the workload runs in kernel, and the motivation from this came from hardware lab detector. So the OS noise runs a busy loop in kernel, and it reads the time in the loop and reports when the two reads of the time are higher than a threshold. So we had a noise. And we had timer lag. That is basically the same idea from a cyclic test, which is a periodic timer that's awakened in the future. And here, the timer lag, because it's in the kernel, it can also report the IRQ latency, not only the thread latency. And these tracers add a new set of trace points that automatize that mechanical thing that we usually do, like enabling IRQ entry and IRQ exit trace points, and then computing the delta. Enabling SCAD switch and computing delta between SCAD switches of a thread, for example. And these trace points, they report the interference of the workload on the interference made on the workload dispatched by the tracer. And the good thing is that the workload, because they are in the kernel, I can synchronize both the workload and the trace and use this to generate better information. I tried to do this first in the kernel, in user space. We can discuss that, but it didn't work because from user space, I cannot automatically access the data in kernel. I always need to do some sort of system call, and this breaks the idea. So, and because it's possible to access this data, you can also, instead of just reading the delta between two time reads with the OS noise, it can also report how many interference happened in this meantime. So just to show one example here, I'm getting to the point now. So this is the output from the OS noise tracer. Just enable it, and it sends a report that looks pretty much as a benchmark tool, not a tracer, right? And gives some useful information, including like counters of interference. For example, this system here was showing hardware interference, which could be detected, for example, by a hardware LAT detector. In this case, they are high because they are a virtual machine. And here is the tracing part where I enable the events and I can say, okay, here this thread found a threshold. And it says that there was an 8 microseconds noise and it was caused by 2 interference. So I just need to go back and boom, boom. Okay, it was an IRQ from timer and a migration thread. So, and that is the value of these tracers. They give you numbers and also some precise and already interpreted data that you could give to a developer. If you are not a RT developer, you can give to a developer, and that's a nice starting point. It's not the end of the journey, then you go do other tracing, but it's a starting point. So here is the tool. The RTLA is an interface for these tracers. So the tracers, they work nice as tracers, but they could also be used as white box testing. So they could report the benchmark to values and report a trace if an unexpected value happened. And during in any session, you can always have this enabled. So if you find like a higher OS noise latency, you can capture that case and do a report with okay, what caused it. The idea of RTLA is doing an intuitive interface because using tracer is not always easy if you're not a developer, right? It is easy, Steven. It is easy. I know, but it can be easier. And this tracer already have a nice set of configs, and making it available for the user is better. But there are things that are better just to do in user space, like setting priority of the workload, saving data to trace. And I'll just show a video of the demo of this tool. If the font is too small, I pasted the link of the demo in the shared notes. So here I'm showing some options. So the RTLA has two modes, the top and the histogram. Here it's patched the OS noise in a top view, which gives you a more interactive view of the summary of the report. And we also have the histograms, and we have some options like using things with priorities, setting the CPUs, like skipping zeros or lines with all zeros. You just skip to make the output clear. And you can do all the tracers configuration from here. You see, then we have I think I'll do timer lat now. This
So
is the
Daniel,
top. Go ahead, Clark.
So that demo that you were just showing with the histogram that skips zeros, that you just zip to the bottom, and that said that the max latency you saw was 75 microseconds. Did I get that right?
Let me show here.
Yeah. So you had
Yes,
2 hits.
yes.
So it's a really quick way for you to be able to say, what's my max? Which
Yes.
is what we're always trying to figure out. Okay, thanks.
Yeah. Just going back to play. Okay, timer lat top it's the same idea, but it shows the RQ, timer latency, the thread latency. And here also the histogram. I'm just reducing the number of CPUs because it would not fit in the screen. Wait a little bit. Boom. Both thread and IRQ latency. I submitted the patch last week, but it already has main pages and things to make it use. But that was like using only as a benchmark, and this is using the tool also to collect the trace, to send it, for example, for developers. So here I'm saying to trace and to save to LPC file. I say to stop the trace if a thread latency is higher than 30 microseconds, and to get a stack trace of the thread that was running when the IRQ happened. Here the benchmark tool is showing the results. It's running a background workload. Here it's just running a kernel compilation in the background. And boom, the trace hit a stop. You can see here on the CPU 20, you already can see that there was a 30 there. And then I can just read the trace that was saved. So yes, it was the CPU 20, and there is a stack trace of when the IRQ happened. It's pointing me to a network stack, which is often the cause of problems and things that we look at and say, okay, here's the problem. But at the end, the noise added by the thread is just 4 microseconds. The vast majority of the noise in this case was the timer interrupt with 23 microseconds. And actually, the thread saw this, but the IRQ didn't. The IRQ latency is just one microsecond. So the problem is in the timer IRQ, and that obviously is just the starting point, right? Now you can use other functions of trace to figure out the problem. I will raise the questions now in the discussion. Just a second. Returning back to the presentation. Stop sharing. Okay. So yeah, the code is fresh. The timer Latin noise tracers just landed on kernel on 5.14. And this tool, following the conference-driven development cycle, the RFC was sent to the mailing list last Friday. The tool is written in C, and it's mostly using libtracefs because the traces are on ftrace. And it's been quite good to use libtracefs. It has good documentation. It's very easy to use, helping to automatize a lot of things. And although it's not using BPF, it will likely use soon. I did some experiments measuring the OS noise with BPF, but then I found some limitations that probably will be overcome in the future, but that led me to do things in the kernel. This tracer used the RTSL code which was presented last year, but I had to postpone the trying RTSL, which is a more robust for the scheduling latency. It has like some academic background showing why that is the worst case and not just one case. And but these two tools are sub-products of that proof of concept. So the proof of concept is already giving us some results. And there are more tools in the pipeline. The RV interface will likely use the same code base. So that's your feedback on here. It will also be important for that part. And that's it. Discussion time. I have some requests, but we can discuss the tool before.
So you're going to do a new paper on a different software development methodology, conference-driven development?
Oh yeah, that works for open source.
And of course, the obvious question is, why did you write it in C and not in Rust?
I asked him that.
I wrote in C. I tried to work first with BPF. There is an EOS noise in the interwebs. It was nice, but at the end, derivating the work from the hardware lat detector was the most precise way to proceed. And that's why I wrote things in C. And libtracefs is in C. It's the tool that worked for me, but if in the future I have to use any other language, I don't have problems. Okay, Ahmed.
Okay.
Turn on the camera.
Without the camera, I will just ask. So I saw the trace in your video, and I always had, and it was also clear that the user space part there, it was not decoded. And I always struggled actually with ftrace regarding user space stack traces, and I just gave up and used perf, honestly. So is there a way to solve this, or the user space stack traces will still be undecoded?
I think that there are two possible ways to answer this. One is these trace points are also available through perf. And if I can use perf and a C way to use the same methodology the perf use, I can do in the tool as well. So it's easy to circumvent this tool and this problem. And that's the idea of having a tool. I'm not creating a new perf. I'm not creating a new trace command. I'm just using the infrastructure that they give me. But another possibility is still have the answer from the tracing side.
Well, the question is, right now, ftrace just does everything from the kernel. I think perf. How does perf get the stack trace from user space? Does it have a user space? Because perf, everything's from perf is done from user space as well. So my question is, if perf could get the stack trace of the user space side, is it doing something special in the kernel? I know I haven't really jumped in and look at the code that's done. I used to use the same code. Peter's on, or Peter's not participating by sound. Or is Arnoldo here?
No, actually, he's got another presentation going on, probably in the next 5 minutes or so on another track.
Yeah.
Because if perf is able to do it, why can't ftrace do it? That's my question would be.
Yeah.
I haven't really taken a look to see what.
The infrastructure for backtracing into user space is there, so you could use it as well.
Yeah.
So basically, it's just something that ftrace needs to fix. And if it's already there. Yep.
Yeah. One reason for me to try to use to make a tool that is independent is that I'm not connected necessarily with a single thing. I can use the best that system can give me. If it's ftrace, it's ftrace. If it's perf, if we can fix ftrace, we can add a PPF.
Yep.
That's the idea. I'm not necessarily connected to a single tool.
So from the chat, Peter has responded. Peter responded with the chat. Basically, what they do is just takes like 1K or so of the actual user space stack and just copies it into the ring buffer, and then perf will just unwind it when it gets to user space. So it's basically just copied. Then that means perf probably has to have some sort of way of looking at the user space code and figure out where things are. I mean, we could do something out of libtracefs, should be able to easily do something like that. We just have to have a new event to say, just give me user space stack, just copy a bunch of it.
Yeah, yeah. As long as I have a way to do a function call and give interpretation, it's easy. But yes, this is in that a thing to make the trace more clear. I agree with that.
Because it's something that ftrace should have, and it's like I've had other people request this, so I think I'll just fix it. Sebastian,
Shouldn't you just be able to lift what they're doing?
Well, the thing is, a lot of it writes right into the perf ring buffer. I just have to do the same to write into the ftrace ring buffer. And the problem with that also is what Peter just said again, performance is crap.
And actually, it would be good to understand where the code in user space is leading us to the problem. But for the trace analysis, it was always enough to me to understand the kernel side.
Sebastian has his hand up too. Are you waiting to talk?
Yeah, I waited. In the video, is it just that you record all kind of features like trace events, and then you try to correlate what went wrong and what it might have been? Or how do you know what event is the bad one?
Because the tracer runs the workload runs in the kernel. When it hits the threshold, it stops and it has the data already available for it to read.
So you have to configure like a network packet has to be sent like every second or so. And then if it's second and a half, your trace hits the threshold.
Actually, here I'm just, I know, I'm not sure if I got the question, but the workload that I have here are two only. And they're specifically made for these tools, which is the OS noise workload in the OS noise tracer, and the timer dot workload in the timer dot tracer.
Okay, so basically you know more or less what you look for.
Sorry?
So basically you know what you're looking for.
Yes, I know what I'm looking for. Other tools can be developed knowing what they're looking for and give you also other let's say metrics. That's also the tool is fresh. The more things will come, and I hope they come.
Yeah, we'll try to look at the code, but didn't get to it yet. Okay, thanks.
Okay, sir. Thank you, Sebastian. John Kaser?
John Kaser?
So I see you asked a question about RT Val, so I thought I'd say a few words. So RT Val has two kinds of modules. It has measurement modules and load modules. Right now, it's not too difficult to add load modules. I've recently added stress NG. There's still some areas of the code where adding load modules is a little bit difficult. But using the load modules for your tool, you know, you'd have everything. You can already easily compile the kernel synced with your measurement module, or Hackbench or whatever load you're using. So we have the concept of the measurement module, and that right now is basically cyclic test. So what we would have to do is extend, I think when Clark and David originally wrote the tool, they had the idea that it would be easy to swap out stuff. I'm not so sure how easy it would be nowadays, but basically we try to write a measurement module that would use your tools instead. So, yeah.
Yeah, I think, you know, it was kind of naive to think that dropping a new measurement tool in there would be easy because everybody has different formats for their output. And, you know, RTVal does statistical analysis based on the fact that on the output of cyclic tests. So we'd probably need to, and the other weird factor here is from RTVal's point of view, is that RTLA is both load and tool rolled into one.
Mm-hmm.
So it'd be kind of interesting to figure out how to make it work. But I don't think it's impossible.
No, and we might want to use, you know, a concept of a third kind of module, which is built into it. But I could see how it could be advantageous for Daniel to take advantage of the infrastructure that's already there. Like, I think it'd be worthwhile to look into anyway.
We
Well,
can
you know,
mimic the cyclic test output, for example. It shouldn't be hard. For example, for timer dot and cyclic test, which are sibling tools. Actually, I tried the histogram. It's somehow based on the cyclic test output.
Anyways, that's all I had to say. Thanks.
No,
I just figured
that's
that
good. And keeping on testing, Daniel Wagner, I saw that you were adding some code to automatize the parsing of the output from tools. How hard is for us to do that for RTLA? And also to connect with Lava.
Yeah. So the thing I've added is basically just that the histogram is dumped as JSON format string. Yeah, so nothing. There's nothing really difficult there. I mean, I suppose this could be easily added or extended to your case.
Actually, in the trace, in the output of the histogram, I put an option to hide some data like the heater or the scale, right, or the values in the bottom, because for me to write some histograms using Glue, that helped me out. Knowing what helps you guys out in the integration, it would be a good thing to me to try.
Oh. Yeah, okay.
Any other suggestion? Otherwise, I will start asking Steven for features.
You're asking me to request features, or
I have some requests from libtracefs.
okay, yes, please. I mean, there's a Bugzilla. Please submit everything you want. Any feature requests in the Bugzilla.
This is a conference we need to discuss here and now.
Oh, you want to discuss these features now? Sure, go ahead. But still, put them in the Bugzilla. I tell you, put them in the Bugzilla because that's where I will look into it. So, what features would you like?
So now on the RFC I've sent, I've added the possibility of using two instances of OS Moise and Thermalite trace. That is good, right? But the reason why I need that, it's because when I dispatch the tool, I create one instance to collect the overview data and one for tracing, right? So I'm always writing twice to the buffer. So and the reason I do that is because this one I'm collecting the data and displaying, right, for statistics. And this one I just let it run until it hits a stop condition and I use it to dump. I cannot keep reading from this because the data is consumed, right? If I could have a way to collect the statistics, the data, without cleaning up the trace buffer, I could just run once. And this would be some cycles.
So you want to basically read. So it's actually a kernel change then, because you want to read that without consuming.
Yeah. Is it a kernel change?
Yes, because you can't read raw data without consuming. The raw data consumption, there's no way to read the raw data. You can read trace files without consuming, and that's done very it's a lot of trick code in the kernel to do that properly, because there's a lot of races. Because you have to, it's the right, and I updated it, so I mean we could read the trace. You could read the trace file, I guess. I'm not so sure if we could do the binary way of doing the same way. Maybe we could add a kernel change to read the binary code without. But that means we have to make a copy. You have to just take a page and copy it, because and hope that if it gets written over, just keep doing it until you get it before it's written over.
Yeah.
That's how fast.
Yeah, interesting. So that would save some overhead. Anyway, the things are working nicely now with regard to overhead. We're using noise tracing. If I put the threshold like 1 microsecond, it's still not reaching the overhead being higher than the threshold. So overhead wise, it's good. It's just a minor improvement.
So I see Masami. I just want to comment because Masami posted something in the Matrix channel or chat saying, the TraceFS, trace do not consume, TraceFS, trace pipe does. But again, those are ASCII. Those are ASCII outputs. We're talking about the raw binary, and right now the only way to get the raw binary is with a trace pipe raw. With the name, as the name suggests, all the trace pipes are consuming buffers. Trace files are not. I mean, I could maybe make a trace raw, and it'll be a best effort to. I mean, if your traces are slow, where the reader keeps up with the writer, it shouldn't be a problem. It's when your writer is much faster than the reader. If you want to try to consume things, so it's going to go into some sort of. We'll have to do, copy the page and check to see if it got written during the copy. If it did, try again.
Okay, so maybe keep 2 instances is the best way.
I mean, I could do that. If, I mean, is it something that's written very fast where you can't keep up?
Yes, it could be. If I have tracing enabled, yes, it could be. Not sure. We need to test the system, but it could be. But that we can always allocate more memory.
I mean, I could try it.
You just have to make the tracer the highest priority process.
Yeah. Actually, I don't think that would even work too, especially if the tracing actually causes enough to do the tracing. Sometimes it has that effect. Well, you have that big event. It causes the events that it's going to record. Then you have an issue. And how big the buffer size is. Like you said, it probably wouldn't be too difficult to create something. That would actually be an interesting exercise. Maybe someone else would like to try writing it if they want to learn that code.
Yeah, yeah. And person that will do this, please file the Bugzilla. And another thing that I'm doing myself is I'm saving trace to a file. I just saw an option to save from a pipe, but I don't want to read from the pipe because the pipe keeps generating data. I would like to save the trace file. I'm doing now myself reading the a page per time, but I'm certainly, you guys certainly have a better way to do this, and we can get out that code from
the trace command library should be coming out hopefully soon. We're slowly doing that, and the trace command library will allow you to record to a trace.dat file, even a live stream or something.
Yeah, that would be good.
Yeah, that's in the works.
Something that is Tom around, Tom Zanuzzi? No, but that's a request that this would save me time, which is for the histograms. I currently don't. I have the histogram, but sometimes my histogram can be smaller than the values that I receive, right? So now what I'm doing is I have a histogram that is the size I wish it's enough, but I still enable the trace event that generates the data I'm creating the histogram, like the thread latency. So the OS noise sample. I use a histogram in kernel, right? But when the value is higher than the histogram, I lose it, and I don't know which is, and I need this to compute the average values, right? What I'm doing is that I'm still tracing the event that I'm creating the histogram, but filtering with a value one higher than the histogram, and still handling those events if they are generated to compute the real max, and not just the max that was able to fit the histogram.
Wait, say that again. I'm confused.
Yeah, so you have a histogram, right? And
Yeah.
the histogram has a maximum value it can store.
Yeah.
Right. But the tools might generate a value even higher than the maximum of the histogram. How do I take note of these values?
You mean from the? You mean from the histogram? You mean the Tom Sanusi's histogram code you're talking about with the max?
Yes. Let's say I have a histogram that stores up to 1 millisecond latency, right? And I have like a 2 milliseconds latency. How can I read that the actually maximum value was 2 milliseconds and not the maximum value stored on the histogram?
I still don't. I guess we may have to take this offline, and you have to show me exactly what it is, because I don't see. I don't understand exactly what you're doing, because I'm like, I don't have this issue. I'm not sure what you mean by setting a maximum value in a histogram. Usually a histogram will just record the maximum values.
Yeah, but if you record all the values, but if there is a number that is higher than the value you can store in the histogram.
What do you mean the value? What do you mean there's a value they can't store in the histogram? You mean you ran out of the max histogram? You mean the size that you hit all the values and you filled up the histogram? Or
no, a value higher than the maximum.
Is there a maximum? I thought it could take any number and just shows it will just put it in there.
You have bucket size of 2048 by default on histogram.
Well, I thought it was a sparse tree. It only fills in.
Okay, that's something that You see,
But that's what I'm saying is like I thought it was sparse. It actually doesn't break it up into like it doesn't say okay here's an allocation and everything fills in. From my understanding was it just puts it into the it just stores it at the value that was given. So if you have 1 and 10,000, it will record just 2 buckets, 1 and 10,000. It doesn't break it up into a bunch of buckets. From what I understood.
Don't you have a maximum number? The time is up.
I don't think so.
Yeah, that's something we should probably fix in cyclic test. Is it's just a contiguous array. The histogram logic theory is, and we should probably make it sparse as
Yeah,
well.
because the one in the kernel is not is sparse.
Yeah.
Okay.
That's why I'm confused. But we'll
So
take this
now you
offline.
need to check. Yeah. So thank you. Well, now we have 10 minutes break. Yes, 10 minutes. I see you in 10 minutes.
By the way, what I would suggest, Daniel, right now, for when you do the break and you do the poll, put in, so the 10-minute is on the hour of 25, I would say. So put in, see you back at *:25 or something, just so people know what that 10-minute is.
In the, okay.
In the poll, I think in the poll you could put in that.
And then, Daniel, if you don't mind giving me moderator privileges.
Oh, yeah.
Should have automatically.
No, don't do it.
Oh, I will give you privilege, and you do the poll. You know already how to do this.
I couldn't figure out what you said.
Do the poll and say that we will be back in the 25 minute. In the minute 25.
Okay.
I'll write you.
With privileges comes the responsibility.
don't see a poll. Was there a poll?
I think it's appeared because I gave presenter to Andre.
Right. So when you took presenter away from me, I lost it. The poll went away.
Okay. I think we still have, what, 2 more minutes?
Yeah.
Hey, Daniel.
To
you
who
have,
should I send the presenter?
you can send it to me, Srivatsa, and then halfway through the presentation, I'll request you to make Sharan the presenter.
Okay, I set you as the presenter. And do you want me to load your slides or?
Yeah, yeah.
Okay, just
Please do.
load your slides.
Yeah, Srivatsa, just to let you know, you can't, when you're ready to switch the presentation, you could actually pick, you could actually pass it to someone. You have that ability. So you just pick them on the left-hand side. And then
I
just,
see.
you could say, make presenter.
Sounds good. Cool. Thank you.
You are the presenter now. Just let flip the minutes, sorry, and start.
Okay. I'm not able to make, I don't see the option to make Sharan the presenter later. I can only give him like whiteboard access. So maybe,
Okay, ask me and then I will jump and switch to presenter if it doesn't work.
sounds good. Thank you.
No problem.
Luckily, the two of you are actually next to each other on the list, so, or not next, quite next, but close. See the fine.
Can you hear me okay?
Yeah, I can hear you.
I guess we can start, right?
Hey, Daniel, should we get started?
Yeah, go ahead.
Okay, perfect. Hi, everyone. I'm Srivatsa Bhatt. My colleague Sharan and I are pleased to present our work on Linux kernel support for kernel thread starvation avoidance. This is something we've been looking into as part of supporting telco 5G low latency applications on the Linux real-time stack. I'll start with a brief introduction to the telco 5G use case and explain how we use Linux preempt RT, and then describe some of the problems we're seeing when deploying these applications in the field. And then we'll discuss some existing solutions to this problem, and then why these solutions don't quite adequately address the problems you're seeing. And then Sharan will cover the design and implementation of a solution we propose called the stall monitor, which is a kernel thread starvation avoidance mechanism implemented directly in the Linux kernel. And finally, we'll describe some challenges and request your feedback and suggestions on how to make it better. So in the telco 5G use case, what we have is a radio access network, or RAN, which consists of a radio tower, as shown on the left-hand side, which sends network packets to a nearby data center running, with servers running the Linux preempt RT kernel. And the application stack involves using Intel FlexRAN, which is a reference implementation of the radio access network software stack, or radio access network architecture. And the FlexRAN software has a processing pipeline through which these network packets go through, and then acknowledgements are sent back to the radio tower. So what makes this a real-time system is that this entire flow of packets, the round trip from the radio tower to the data center and back, has to finish within a fixed time budget. And that budget is governed by the 3GPP specification for 5G. What it means is, if the call flow doesn't complete within that particular time budget, the call flow is considered failed and has to be retried, which is cost prohibitive because the 5G spectrum is expensive. So this is why the application stack demands predictable real-time response from the underlying platform. What this means for Linux is that when RAN vendors try to evaluate Linux platforms to see if it works well for 5G, they expect a scheduling latency as measured by cyclic test to be under 10 microseconds. But the 5G use case actually has even more stringent configurations where any kind of sleep and wake up latency is unacceptable. So the FlexRAN software stack is designed using Intel's DPDK, which allows user space applications to directly poll for network packets and process them completely in user space without ever having to take a round trip to the kernel. So that helps us design these low latency applications. So let's see what kind of issues arise when deploying FlexRAN-like applications on Linux preempt-RT. So on a typical Linux system for FlexRAN or RAN kind of workloads, we start by dividing up the available CPUs into no-hertz full isolated cores designed to run the, or designated to run the real-time application. And then the remaining cores, what we call housekeeping cores, run the OS background threads or essential services and even non-RT workloads. And the y-axis shows task priority, and higher up vertically, the task has higher priority. So for instance, here I'm showing the L1 app, which is the layer 1 processing of FlexRAN, running as an infinite loop. That is a CPU-intensive DPDK-based application with high real-time priority SCED 5490, which means it's higher than pretty much any kernel thread in Linux, right? At the same time, on housekeeping cores, we have essential system services like SSHD, systemd, networkd, and so on. And then also Kubernetes control plane tasks, including kubelet, containerd, dockerd, and so on, right? So in this scenario, whatever you do on housekeeping cores can actually end up waking kernel threads on every CPU. For instance, we see this K thread getting woken up on the isolated core running the L1 app with a lower real-time priority SCED 541. So in this picture, the solid boxes indicate tasks that are actually running, whereas the dashed box indicates tasks that are runnable but starved. They don't get any CPU time. Right. So in this case, the K thread is actually starving because the L1 app, which is running on the same core, the isolated core, is a high priority real-time task, and it never yields the CPU. It's very CPU intensive, right? So that leads us to our problem statement. Essentially, kernel threads that are starved in the system lead to cascading lockups and cause a system-wide hang eventually, because the scenario can happen such a way that these kernel threads or whatever invoked these kernel threads hold resources that other applications need. And because the kernel thread doesn't make any more progress, it's permanently starved, so it locks up the entire system. Everybody waits on that resource, right? What we'd like instead is to have an OS that remains stable, meaning all its kernel threads, essential services, everything makes progress and remains available, while limiting the fault domain to the real-time application itself. So the real-time application, if it is misconfigured or misbehaving, it can starve or experience a crash or abort or whatever, but the OS itself must remain stable, and we should be able to access it and troubleshoot it. So let's see a specific example of this problem, how this comes about. So a classic reproducer that we have is container destroy. It creates a hang immediately. So the reproducer is essentially just run a high priority CPU hog, real-time CPU hog on an isolated core, and then create and destroy a Docker container on a housekeeping CPU. Let's see how this creates a hang. So here I'm showing top output from this particular scenario where we're looking at CPU 3, which is no hertz full and isolated. And it's running the loop RT task, which is a high priority infinite loop with SCED 5455, right? And at the same time, we also create and destroy a Docker container from one of the housekeeping CPUs. So as you can see, there are two runnable tasks on CPU 3. One is loop RT, of course, and the other one is kworker/3, right? The kworker/3 is a per CPU kernel thread, and it can only run on CPU 3, so it cannot be migrated away. That also woke up on the same CPU. And on the left-hand side, you can see that the priority is actually lesser than loop RT, because kworker is a normal priority task. It's not a real-time task, right? And as you can imagine, the loop RT program continues to make progress. You can see that the time column shows that loop RT has been running for 1 minute 32 seconds at the time I took the snapshot. But kworker/3 is completely starved out. It's stuck at 0 time, 0 execution time. Right? Let's see how this comes about. Right? So essentially, when we destroy a container, you can see the stack dump from a Docker-D, where it's trying to invoke this function called rollback registered many. Right? That's part of the network namespace teardown mechanism in the networking subsystem. And that in turn invokes flush work, which wakes up per CPU kernel threads on every CPU to participate in the network namespace teardown. However, we know from this picture that the flush work will never complete because the kworker on CPU3 is never going to make any more progress. It's permanently stopped, right? But that's not all. In fact, it turns out that this particular call flow, which calls flush all backlogs and leads to the kernel threads getting woken up everywhere, holds the RTNL lock, which is a very popular lock in the networking subsystem. So what this means is, after this particular point, any other task, any other application that is requesting kernel services in the networking subsystem, which needs the RTNL lock, will also get stuck in uninterruptible sleep state, D state. So here I'm showing a stack trace from systemd network D, which is trying to send a socket message, but ends up waiting on the RTNL lock. And it'll never get that lock because the entire system is stuck in this particular state, right? So similarly, we have other applications also getting stuck in the same path, which leads to the cascading lockup that I was talking about. We've seen this issue with SSHD, systemd, network D, the package manager, and pretty much anything else that touches networking. So essentially, networking is out, which leads to the hang, right? But then this problem is not limited to the network namespace destroy code or the networking subsystem in general. We have seen the same kind of issue where you wake up kernel threads everywhere and then have a hard time making progress because you have CPU intensive real-time tasks running. And we have seen this issue with ext4, C groups, ftrace, sysctl, and a variety of other subsystems, right? So we'd like to have a generic solution to this problem. So let's talk about some existing solutions to this problem. And before I jump into stall-D, I want to quickly mention that the real-time throttling feature in Linux is completely ineffective in solving this problem because it does not protect low-priority real-time threads from starvation issue. It only caters to non-real-time threads. Whereas in Linux, we have kernel threads that are both real-time and non-real-time, right? So that's a no-go. Stall-D was introduced by the Red Hat team, Daniel, Yuri, and Clark in last year's LPC in the real-time microconference, precisely to solve this particular problem, right? So stall-D is a user space daemon that keeps monitoring the system for starving tasks. That is, those tasks that are runnable but not getting any CPU time for an extended period of time, and then gives them temporary priority boosts using the sched deadline policy. And the great thing about stall-D is it performs this boosting and revives the system by operating within user configurable bounds of OS jitter. So for example, a user can say that I can give you like 10 microseconds of CPU time in every 1 second period, and you can do whatever boosting you want to do to keep the system healthy. And stall-D will honor these bounds, right? In fact, stall-D, this particular problem is so prevalent in the RAN application space that stall-D has become critical to these deployments to maintain stability. In other words, without stall-D, these applications would not have any meaningful uptime. So we'd like to really appreciate and thank the Red Hat team for developing and contributing stall-D to the open source community. However, deploying stall-D and RAN applications in the field, we have come across a number of limitations of stall-D that actually make it hard to use in practice. Take scalability, for instance. Stall-D scales in principle, but not in practice. The reason being, stall-D has or creates a thread, a pthread for every CPU that it wants to monitor and potentially boost starving tasks. But then the use of isol CPUs for real-time workloads means that all of stall-D threads are bunched together and forced to run only on the housekeeping cores. So for instance, if you have a 20-core Linux system with 18 of them isolated to run the real-time application stack and 2 cores left as housekeeping CPUs, potentially 20 stalled threads are all waiting to run or competing to run on the 2 available housekeeping cores. So it doesn't scale with the number of CPUs. What's even worse is stalled can get starved itself. So stalled is a normal priority program. So it has to compete for CPU time on these housekeeping CPUs, right? But then housekeeping CPUs are not sitting idle. Like we saw before, it runs OS housekeeping tasks and also non-real-time workloads like the Kubernetes control plane. So it has to, so stalled may not get sufficient CPU time on these housekeeping cores to do all the monitoring and boosting that it needs to do. Attempting to solve this problem by making stalled a real-time priority application is actually risky because depending on the user configuration of stalled and how aggressive that is, it can so happen that all of stalled threads potentially end up consuming most of the available CPU time on these housekeeping CPUs, thereby starving out other tasks. In other words, stalled instead of becoming a solution, it can cause the problem itself and starve out other applications. Stalled has a bunch of other issues. For example, its logging is actually unreliable. So it stalled logs its output to journal control logs via systemd journald, but then journald itself can get stuck on ext4 code paths, right? So in the best case, what we've seen is stalled continues to make progress in the sense that it monitors and boosts starving kernel threads, but then its execution flow and boosting decisions cannot be traced back to the logs because journald is not logging anything. But in the worst case, we've seen an even kind of more severe instance of this problem where if we increase stall's logging to get more insight into what's actually happening, stalled can get stuck trying to write to this IPC socket to journald. And therefore, stalled also stops monitoring and boosting kernel threads, making it completely ineffective in preventing a system hang, right? One final point I want to highlight here is there is a trade-off between the response time from stalled to prevent a starvation event and its CPU consumption. Because stalled has to keep looking at proc-scat debug file and parse it to understand if there is a potential starvation condition happening, and it does this from every single thread in stalled, it can be pretty CPU intensive. So stalled offers a single-threaded mode where you can choose to do all of the monitoring and boosting from a single thread of stalled. But then this is a tricky trade-off in practice because as we saw before, most of these hangs occur because of per CPU k threads becoming starved on every CPU, right? So that means a single thread of stalled has to potentially boost, monitor and boost multiple kernel threads at the same time. So it may not be that good of a trade-off for response time. So it can still create a hang.
Can I just make some, sorry, can I just make some updates on these? These things were true. So to say, not defending, stalled is not the best tool in the world. It was made to be someday overwritten by something else, like using TL servers, this on top. But some of these topics here, they are not, let's say, updated, right?
I see.
So the single-threaded mode, it's now, that trade-off of CPU consumption response time, it was lifted off. It doesn't exist anymore. So it's performing as well as you don't need to use the multiple threaded anymore. It performs as precise as the single threaded version. This problem was solved some months ago already. So,
I see.
And now that fixes the first problem. So not saying that, not invalidating any reason, just clarifying points, right? So now stalled works, it's one thread per any CPUs. So it can scale better. Regarding stalled starving itself, now that it's a single thread, you can easily set it to run as a scat deadline. And adding priorities to a process, that's a long-time discussion in the kernel. It's not the responsibility of the kernel, it's the responsibility of the user. So setting RT priority now that the multiple thread problem were fixed should not be a problem. And we have been using it for a while. And actually, setting the real-time priority fixes the problem of if stalled uses, if you use like logging using, let's say, journald, if stalled logs in a mutex that's depending on there, If stall D has a higher priority, as it doesn't consume much CPU as it used to consume, it can run safe. It would unlock that log because of the priority inheritance. Anyway, you can use log directly to the kernel. You don't need to use that kind of log anymore if you don't want to. So many of these problems pointed here were fixed in the latest version, just to clarify.
I see. We'll definitely check that out. Thank you. Cool. Given our understanding of limitations of STALD at the time, we felt that many of these limitations actually trace back to some design decisions in STALD, including something as fundamental as the decision to implement STALD as a user space program. So we decided to seek a better solution to this problem that addresses all of these limitations in the field. And we came up with something we call the stall monitor, which is essentially STALD-like boosting and monitoring of kernel threads in the Linux kernel for starving kernel threads. And I'd like to invite Sharon to go over the design and implementation of stall monitor. And Daniel, can you make him presenter, please?
Just a second, finding names in the list. Okay, you're the presenter. Someone else was faster than me.
Yep, thank you. So with these limitations in mind, we had certain goals that we wanted to achieve, and we'd like to mention those goals and why we think the kernel is suited to meet them. So firstly, we want to prevent kernel threads from starving by having an in-kernel starvation avoidance mechanism. We're really attempting to compartmentalize the fault domain. We want to avoid situations where these workloads causing kernel threads to starve result in the entire system hanging up. We want to be able to keep the OS stable and limit hangs to just the application threads. The second goal is to ensure scalability. So the only things that become runnable on these iSolve CPUs other than the application hoggers are the per CPU kernel threads. And they are the ones experiencing starvation. So the starvation detection problem is naturally per CPU. And if we have per CPU scheduler hooks to monitor for starvation, that will tend to scale well. There's no need for system-wide monitoring or cross-CPU coordination. We want to be able to monitor and boost efficiently. We want to avoid unnecessary periodic monitoring. So if we can hook on to scheduler events like tasks waking up or tasks being taken off the run queue, that gives us the opportunity to make these decisions efficiently. Guarantee responsiveness. We don't want to be in a place where the entity responsible for starvation avoidance is itself starving. So because the scheduler will be aware of a task becoming runnable, we can be sure of getting a chance to start monitoring. So keeping these goals in mind, we have certain features within the stall monitor. So each CPU will keep track of only starving kernel threads. And not just that, it will be the kernel threads that are meant to run only on that CPU. So we'll have one HR timer in each CPU, and that HR timer will run only if there are kernel threads runnable on that CPU. And while it is running, it will run for one of two reasons. It will either run to detect starvation using the starvation threshold time, or it will track how long a boosted task has been running with the elevated priority. Then we given time, and we want to do the boosting or deboosting in hard IRQ context of the HR timer. We don't want to hand it off to soft IRQ and wait for another kernel thread to run because that's the problem we're trying to solve. And finally, similar to stall D, these values like starvation threshold time, boost duration time, and the shed deadline parameters like runtime and period will all be user exposed and user defined through maybe sysctl, so that the jitter that may come in because of boosting or deboosting doesn't surprise the user. So I'd like to quickly go through the flowchart of the algorithm. So in enqueue task, when a task gets added on to a CPU's run queue, we essentially check if it's a kernel thread that's about to get added. And if it is, then we add it to a starvation monitoring list, which is another per CPU data structure. And we start off the HR timer in starvation detection mode. That is if it's not already running. And then we proceed to finish rest of the enqueue process. And when the HR timer callback, when the HR timer expires, we receive the interrupt and we enter the callback function. We first try to figure out what mode we were running in, were we in starvation detection mode or were we trying to deboost? In starvation detection mode, we essentially look through the CPU starvation monitoring list and see if any of the kernel threads are starving. If it is the case, then we replenish the same timer with the boost duration. If there are no starving kernel threads and if the starvation list is empty, then we just stop the timer. And if there are, then we just replenish the same timer with the starvation threshold time, and we come back again to see if any of the tasks have experienced starvation. So IRQ exit. So we attempted to do the boosting and deboosting using sched set attributes, and we initially attempted to do this in the callback function, but we noticed that the priority inheritance code doesn't allow us to invoke this function from interrupt context. So we waited for the hard IRQ flag to be masked in IRQ exit and then invoke this function. So this is still technically in interrupt context, and we know that this is not the right place to do it, or perhaps not even the right API to invoke this, to do boosting or deboosting. So that is a segue into what we seek from the, because we want this to happen in hard IRQ context, what is the right way to invoke this? Are there better alternatives to doing this boosting and deboosting? We also thought if we should use CPU stopper threads, which are shed 5499 to achieve this. Some of the other questions we have is, do we restrict the monitoring and boosting to ISOL CPUs alone, because that's where the starvation is? And we also want to evaluate how much latency does this introduce, because the starvation algorithm is running in hard IRQ context, and we're also adding kernel.
Yuri has a question. Like, have him.
Yeah, sorry, I was just so that I understand completely. So you are doing this bit in the isolated CPUs. So basically, the CPUs that are running the actual workload that you care about are also running, I mean, potentially basically setting timers and doing those things as well.
Yes, this happens on the ISOL CPUs as well, but all this will run only if there are any kernel threads runnable on the ISOL CPU itself.
Yeah, but then how do you guarantee that all these happens like in less than, let's say, 10 microseconds, if that's your threshold for meeting the workload requirement? Because basically, I'm telling you this because we went through, I think, all these type of options already. We stole and actually I'll post in the share notes something that I posted upstream in the Linux kernel mailing list kind of last year. Then I didn't have time to work on further. But then we realized that if you are, I mean, the isolated CPUs are already running something that doesn't want to really be interrupted ever. And I'm just worrying that by doing this type of calculations and actually adding timers on the same isolated CPUs, you're basically breaking the assumption of something that doesn't want to be interrupted ever, right?
Yeah, that's why StyleD runs it as a thread and not as a per CPU.
And on the housekeeping CPUs, so that basically all the overhead that you pay for running the StyleD monitor, it's only paid on the housekeeping, and also for example, the set scheduler calls. Also, the overhead associated to those calls are only paid by the housekeeping CPUs. Basically, the only overhead.
So one thing I want to mention, from what I understand from when they showed this to me, was that this is all configurable, because you don't need even, I mean, there could be a timeout, but I guess you can configure when this happens. Threads are only woken up at certain times, correct? So, or
it's the problem is even before this. It's where to put the workload, right? So with StallD, you are better. Let's use a parallel, RCU, a nice parallel. With RCU, we have per CPU data processing, which are the processing of RCU callbacks, right? One step on the tuning of this kind of system is moving RCU callbacks out of the CPU. Why? Because you don't want noise on the CPU that you're running the busy loop. The busy loop is your fast path. That's the thing that you care more about. So we offload the process of RCU to isolated CPU. And we also have another option on RCU, which is RCU no CPU pool, that instead of relying on IRQs on isolated CPU, a thread pools for need of trying to run RCU callbacks on the callbacks offloaded threads. StallD is the same parallel. You guys' solution of trying to move workloads to the CPU will make StallD work disappear from top. But you are just moving it to the critical path, which is the isolated CPU. Same tuning will be required for this. So you have the problem that RCU had, you have callbacks offline, you try to do things without creating CPU per CPU IRQ, and boom, you have StallD back.
Right. So
about this use case.
right. So note that if the application is running on isol core and you have a kernel thread that becomes runnable there and gets starved, at this point, we have to boost it one way or the other, right? So we will take some time to run this kernel thread, whether you're using StallD or stall monitor, whatever it is, right? And what we're aiming for is the amount of time that kernel thread runs is actually user configurable. If it's, let's say, 10 microseconds in a 1 second period or whatever, right? And what we're, I think, talking about here is the additional latency that the stall monitor itself introduces by, noting down potentially starving kernel threads and so on. So, right. So one thing that could be done is try to reduce, first of all, evaluate how much latency that actually is, and then try to reduce that. But then the other thing that you brought up with RCU is actually another stream of investigation we want to take up, which is, why don't we just fix the subsystems that are creating these kernel or waking up kernel threads on isol cores that didn't even participate in whatever mechanism was going on? For example, the container destroy, right? The isol core had nothing to do with the container creation or destroy. So why did we even wake up those kernel threads? So in a way, enhancing the no hertz isolation mode so that you actually keep that task running. So you don't have to do any kind of boosting or have starvation events. But then the problem is, this is actually a widespread problem. You have to fix many, many subsystems. So this is more like a solution today to actually address the problem.
But the point that we are raising is that we know that the overhead that you guys are editing with a per CPU time is higher than the overhead that StallD is running. Because StallD only sends a schedule API to the isolated CPU.
Both are the wrong way.
Yeah, I agree. That's why StallD is user space. We can throw it away in the future.
But really, what I really do not get, I mean, how many man years have been spent on developing StallD and StallD next generation and whatever, instead of actually looking at the underlying problem and fix that? I mean, it's not rocket science. Most of the pain points are known. And there are patches actually floating around. They are shitty patches, but they could be polished up. So we waste, again, resources on things which are completely bonkers. Why?
That's why
fixing
you use StallD. That's why StallD is user space. We don't need to care along yet longer.
You're still putting a serious amount of resources into StallD.
No, not yet. Not yet anymore. Not yet. It's basically cleaning up now.
Maybe one thing that can be added. I completely agree with you, Thomas. I personally consider StallD like mostly a debugging tool than a proper thing that can be kind of relied upon on production. So what we use it for in the early development stages of basically the same type of applications is to understand what was actually starving on isolated CPUs and then look at the actual problem and fix the problem in the kernel. And then basically what we use it for now is that if StallD actually logs that is boosting anything, that's the problem, and we need to solve it in the kernel.
It's a band-aid in production.
It's a
nothing more.
band-aid. It's a
That's
band-aid.
pretty much what this other guy who was doing this full isolation mode thing. I mean, the patches are horrible, but he actually has some instrumentation in the entry code added. He wanted to add that, which signals that there's a violation of the full isolation mode, which is nice because you can have a trace point there and you can figure it out. So you don't need even necessarily install D and just use existing infrastructure to decode that. But then there were patches floating around for various things, like I did some of them myself versus RT, but then we got other solutions because the memory management people didn't like it. And I recently got an email from someone, oh, what happened to your patches versus VM, whatever it was, swap or something, which runs a worker on all CPUs, which is stupid because you can do exactly the same thing on the housekeeping CPU. You just need locking around something which is not locked today because it's strictly per CPU. But the patch and there have been a lot of attempts to fix the real fundamental underlying problems, but they all went only half the way. So I mean, really, what's really wondering is a lot of people are interested in that no-heads full mode, and I was doing the groundwork with Frederick. I don't know how many years ago. It's at least 15 or something like that. But we're still at a point where we just are not able to actually sit down and say, hey, here are the fundamental problems, here are the solutions, and then fix up the stupid subsystems one by one. I mean, we're doing the same thing with RT for exactly that time frame, or longer, and it's the only way to actually get something done. Because whatever you do, whether it's stall D or photon D or whatever, it's going to be a band-aid which is just not working well. And as Glenn Elliott said on the chat, I mean, you really can run the thing without all these bells and whistles, because I was analyzing some of the 5G crap as well, and it actually spends a reasonable amount of time in polling, even if fully loaded, in user space. So you can really grab some percentage of the runtime, and you can do that with CPU deadline today. So I have a hard time why people really try to solve problems the wrong way around, and then are happy that they have the next solution, which is not helping anything. It's just making things worse.
We agree. And when we hope to throw away something someday in the garbage. And that's why it's in user space. We don't want to create any thing that connects us with the future, you and I. And we don't want to create a future for SCADAML that we will have to carry along the way for years. That's why it's in user space. We just can throw away. And we also believe that no hurts full no hurts full is the way to go.
Right.
It's a
So just to echo Daniel, even though we try to implement this in kernel space, we don't think I agree with Thomas. This is not the final solution. Like you said, we need to fix the subsystems, or even the task isolation patch set, whatever makes no-hertz actually work well for these workloads, right? So are there some major design problems you see in that patch set in terms of adoption? So it's been floating around for a while now, right? So what do you think are the roadblocks? One thing I immediately saw is it needs the application to modify the application to be modified to use, process control calls to actually say when it goes to no host mode or isolation mode.
I mean, that's really a minor problem. I mean, the main issue is that we know, and a lot of the things which cause unnecessary workarounds or unnecessary IPIs are well known to everybody who is using NoHats full for how long. So, but why are we not sitting down and actually having something like the RT patch set in as an external collection of fixes which actually tackle the real problem, and then go and gradually merge them into the mainline kernel? I mean, that's way better time spent than anything else. So I just compare it to the RT problem. Oh, we could have done RT by an RT daemon 20 years ago, right? Maybe, maybe not. But that wouldn't have solved the problem.
But we did have this iPipe thing.
Tried that.
Okay. The time actually the time is up for 5 minutes, for 4 minutes. We can continue discussing on the mailing list.
So I can pitch 4 minutes longer.
Moderator fail. Sorry, guys.
Yeah, sorry.
I was caught up in the discussion.
Look. We can scout this time from the polls. And vai André, vai Brasil. I will send you.
Bora. Hello, everybody. Hello, Thomas. Hello, Peter.
I made you the presenter. You can select your slides.
So, oops, not slide. Okay, better now. So, welcome, everybody. Thank you for attending my FuTex talk again. So, just a reminder why I'm working on FuTex 2. Well, basically because the current interface will not get new features, and me and other developers, we are trying to make FuTex work better with more modern workloads or new features. And the issues that we're trying to solve here are basically normal awareness. We want to support variable size for FuTex, not only 32 bits, and we want to be able to wait on multiple FuTex. That is the most important feature to me because I propose interface to wait on multiple FuTex on the current syscall, but then it got rejected, and people said to me, hey, if you want to merge this, you need to develop a whole new interface. And I say, why not? And here we are. So this session is to get to have a look on this interface. This is the most important part of the syscall because it needs to be stable. And yeah, it's just an overview of what we are trying to solve in this interface. And how do you get this interface merged? So FuTex.c is quite a long and complex file. And the first step to get new things there is to do a refactor. And thank you very much, Peter, for stepping up and doing that. Peter already. And can you hear me? It said that I lost. Hello. Can you hear me?
I can hear you.
Oh, okay.
You froze a little bit, but now you should be fine.
Okay. Can you see me again?
Maybe if you're having network issues, or do you have network issues? If you're having network issues, maybe you probably don't want your video on if you're having network issues.
Okay. I'll turn off again. Okay, but the voice is okay, right?
Yep, we can hear you.
Cool. So, cool. So the first step is to do the refactor, and this is done, I think. And and we are going to reuse most of the code of the FuTex. We are not going to re-implement the FuTex code base. No more multiplexing. We're going to have one syscall per operation, and we are going to merge smaller patches. So the first patch that I'm working on, that is, as I said before, is the weight on multiple, and this is we did a lot of progress for now, and this is the interface that I proposed in the beginning of the month. This is the interface that Peter resent on the mailing list 1 week ago, I believe. And for this interface to get merged, I believe that we have just 2 small points to debate, to discuss. So just initially an overview of how the interface looks like. So the first argument is, oh, Peter, you can hear me?
I don't know if Peter is.
I can hear you.
Okay.
Yeah, we can hear you.
Yeah, we can hear you. I don't know if Peter has his mic on or mic on. He's been just replying in chat.
Oh, okay. So maybe ask Peter to refresh. I don't know. Well, okay. So anyway, so this is the first argument is a pointer to an array of waiters, and then the second argument is the number, the length of the array, and then the flags, because every syscall needs a flags argument, and then we have the timeout argument, so we don't wait forever. And this is the structure where we store the waiter information. So the first argument here is the expected value, as in the full text weight. Each waiter has expected value. And
I'm
here you
actually, can you hold a pause, because Peter's illustrator is telling me he can't hear you.
Okay.
I mean, everyone else can hear him, so it's actually, it's Peter's side. Maybe you should log off and log on again. Wait, do you hear now? Or no? Oh, maybe Peter will just have to go back and watch the videos.
Wow. Okay.
Yeah. Continue, I guess.
I was looking for the Peter input actually. So.
Oh, so if you need his input, yeah.
Yeah, I would like to give him another minute if possible.
Yeah. Okay. He's logging off and logging back on again. And worse comes to worse, he could watch it live on YouTube.
Okay. Do you mind messaging him? Like.
Yeah,
okay,
we are.
good.
Yeah, we're messaging.
Okay.
Yeah. So Peter, let us know when you hear things. So we're all waiting for you. Well, actually, he can't hear me, so I have to tell him.
Okay.
What if I should just whistle Jeopardy's music while we wait for him?
Please don't. I'll mute you, dude.
I beat
Someone
you to
already
it.
did. Now it doesn't seem like he's even replying on IRC.
And no worries, Andrea. We have a large pause after this topic, and we can use that time.
Oh, okay, perfect.
It's not a problem.
So I will move on then. Okay. So
I mean, if you want to wait for Peter.
Okay.
We can manage the time. Don't worry.
Hello, Peter. Can you hear me? Since that is working. Cool. Let's go. So as I was saying, here we have the expected value, and you can see that we are using 64-bit here because the new interface should support that. And here we have 64-bit for the address instead of using a pointer. I will explain that later. And now we have here we have the flags, because each waiter can have individual flags, because each you can have shared full texts and private full texts on the list, and the reservoir field is just for padding, but it can be extendable. So the first point of discussion is about the timeout, because internally on the kernel side, we work with unsigned 64 for storing the time. And the first thing that we do when we call full text syscall is to convert from timespec to K-time. And I believe that every syscall will actually do that. And while timespec is like POSIX, is ISO-C, is the standard, Peter suggested that we could move on and just use U64 for now on for new syscalls. And yeah, this is my first question. Why not, or why should we move on that direction? Or is everyone okay with using unsigned 64 for timeouts for now on?
I mean, this is a battle I'm fighting for years now, and there's this POSIX purist camp which says, no, the world consists of time specs. Even if every user space programmer hates time specs with a passion, because you always have to do the normalizing. If you add stuff or subtract stuff, it's a real pain. So most people, what they do, if they want to do math on time specs, they convert it to nanoseconds and then convert it back to a time spec, which is really, really brilliant. But it's POSIX. The religion works. So yeah, I'm all for going for a U64, and I really don't care if that doesn't work. If it stops working in 500 plus years from now. So yeah, I mean, I gave up last time. I'm not going to fight that battle to the end.
We could always make a glibc or something where either you pass into the kernel a time spec and have the libc pass in time and do the conversion for you. That way it would work after that time period, 500 years later from now.
Yeah, whatever. So I think we should just go with the times with the 64-bit, not the. We don't want to have the compat versus a non-compat time spec problem. We really want to have the kernel time spec, which has a 64-bit seconds value for new syscalls, and then yeah. So that's it. Because what I fear is if we really go for the U64, we're going to have a long time until glibc people or whoever will actually give in and agree, and we have to collaborate with them on those interfaces anyway. So the much I hated, the most practical thing is probably just going with kernel time spec, which is a 64-bit seconds member, and be done with it. I mean, yeah, it's not pretty, but yes.
Okay, thank you for your input. Yes, the syscall supports the 64.
On the chat, the question is whether to use absolute or relative timeouts. So actually, aren't we want to have both? So our application scenarios where we really want to go with an absolute timeout because you want to follow along a periodic timeline, and that's a pain to do with relative timeouts. And then we have also the interesting problem of what the old Vutex the old Futex, one of the Futex operations, I think it was Futex wait, it supported only relative timeouts, which violates the POSIX spec. Because actually, the POSIX spec says it's an absolute timeout on PZ mutex wait timeout, but then due to the kernel implementation, this was converted into a relative timeout, which is not affected by clock was set events, and people really got into trouble for some application scenarios until we actually provided a variant which lets you select what you want to have.
Okay, cool. So I believe the decision is to move on with time spec 64 and use absolute timeouts, right?
Right,
And,
absolute timeouts and selectable between, as we do now for most of this, the POSIX functions, the Futex operations. We have either
monotonic and real clock, real time, sorry.
Which is good enough.
Okay,
I don't
cool.
need a clock argument for that.
Oh, sorry, I meant real time, not real clock.
Yeah, real time.
Clock
So,
real time, yes.
yeah. So I'm not. I mean, the other option would be to actually hand in a clock ID as we do for the
POSIX clock calls.
POSIX interfaces, the time-related interfaces. It's not the worst thing to think about, because if you look at what's coming in various application scenarios, like related to time-sensitive networking, and they talk about, yes, I hate it, but it's also a real problem. They need to have clock tie variants or PTP time variants, which are completely disconnected from clock tie and clock real time. So it might be actually worthwhile to think about handing in a real clock ID instead of handing in just a binary flag, whether real time or monotonic. It shouldn't be hard to do that, so you just have an extra argument to the syscall, which is fine, because we only have 1, 2, 3, 4, and 5 is fine.
Okay, but why would that be better than the flag? I think I missed that part.
Because you then can, well, in the first place, you only support clock real time and clock monotonic, but we can then extend it to arbitrary clock IDs.
Okay, I see.
So for the benefit of those of us trying to take notes here, I lost what, I don't know if there was a decision made or a recommendation made on whether we're going to pass in a U64 time or whether we're going to use kernel time spec.
So we stick with the time spec.
Okay.
As Arne pointed out, there's another 32-bit problem. If we go for U64 nanosecond scalar value, then on 32-bit we can't pass it by value. We only can pass it by reference, which doesn't solve the problem, because then we again end up with compensor scores, which we don't want to. And we have the glibc and the holy time spec religion camp hating us. So we rather make progress and use something they are happy with. But the other thing we just talked about the clock ID, I think that's more future-proof than just having a bit value which says monotonic or real time.
So you're talking about adding an argument to Futex wait V that is the actual clock to be used?
Yes.
So flags and then the
Yes,
clock ID
flags-
and then
flags is
a time.
mostly related to the Futex itself, and
Right.
then the ID is
So
actually
don't,
related to the timeout.
yeah, don't overload flags with a clock ID. Do that
Yes.
separately.
No, no, it can't fit because of the other magic clock IDs we have. So I think that's the most flexible solution for the future, because we are going to see interesting notions of time in our systems in the not so far away future. The much I hate it.
Okay, cool. So I think we can now move to the next topic, which is the structure of the waiters. So as showed before, this is the proposed structure to store the waiters. But people pointed out in the mail list that this will waste memory for 32-bit applications, since like 1/4 of the structure will be empty. So the solution to that is to have this structure here on the right, on the center of the slide, where you have, of course, the EU64 value, and then you have the pointer for the address, and then you have your flags. And it seems that people still run 32-bit user space to save some memory, and going on the other way around will, of course, use more memory. And this is on the other way of the goal of running 32-bit user space. So any feedbacks? Can we go with this structure, or even better, Peter sent another solution for the structure. And yes, so I would like to get feedback about which layout of the structure we should use.
I'm not convinced about how it saves so much memory argument. I mean, what are we talking about?
So running 32-bit code obviously saves memory. Saving a few bytes on the Futex weight structure does not.
Yes, but does it really matter?
So first of all, the structure that you have on the slide doesn't actually work on 64-bit. So we need to have padding anyway. Then it gets complicated, because then we need different amounts of padding.
Yeah, but the original proposed one works on both, right?
Sorry, can you repeat?
The original proposed one, the one you had in the previous slide, and which is strike through on this slide. I mean, it just works on both.
Yes, it does. But the problem is
it costs 4 bytes per array entry.
Yeah.
Yeah.
This is.
Where's the freaking problem?
So I'm sorry, I think it costs 8 bytes because you also have the reserved field in the previous structure. So it's going to be 1 whole kilobyte because you can have 128 of the structure. When I was benchmarking this a couple years ago, I think the biggest contention was in the copy from user, and this is what we'll be doing copy from user from. So I think this 1 whole kilobyte might mean something.
What's the maximum array size we have?
128.
128.
Yes.
So we talk about 128 times 4 byte. right?
8 bytes.
4 bytes. I mean, the reserved flag is not going away. Really.
So the structure he put on the slide is daft. It should be a U-long value, U-long, U-adder, if you're going compat.
Yes.
And in that case, you take 4 bytes of value and 4 bytes of U-adder.
And you want the reserved field. I mean, it's not going away for compat. And it's we shouldn't decide. There's a clear thing that we shouldn't. I mean, yes, for the structure we could get rid of the reserved field. So yeah.
So then you get 12 bytes times 128.
Yeah. So if we stick with U64 and U32, we have 8, 16, and 4 megabytes, right?
That's 24
Well,
against 12.
You get a hole in that structure due to alignment constraints. So you'll get 24 bytes anyway.
For the array.
Yeah.
Yeah.
So
if you do compat, a U32 value, a U32 address, and a U32 flags, then there are no alignment constraints, and you're to 3 4-byte words, which is 12 instead of 24, which is half.
Right.
But would it be was there alignment constraints on 64-bit?
Because the
alignment
structure
constraint is
has.
there. The alignment constraint is there as soon as you have a U64 member, whether on 32 or 64-bit.
Because structure alignment takes the biggest alignment constraints of its members.
Right.
And the performance argument, I'm still not buying it to optimize for 32-bit machines, because 32-bit machines are the ones where people don't care about performance, because we only care about cost at this point. Nobody cares about micro optimizations for 32-bit. So I don't think that the mem copy speed is of any value. The only optimization that I can think of as important is making the code look the same so we can share the implementation between the two.
Like even Microsoft is ditching 32-bit, right? For Windows 11?
Yeah. Well, you can still run 32-bit applications, and everybody does. And we also do, but 32-bit applications do not have to be faster than 64-bit applications. That's not something we should optimize for.
And okay, and so about the extra memory, in the end is not so much memory. This is the conclusion.
Yeah, Trevor is saying he's stuck on 32-bit machine, is interested in performance. So
that
really,
may well be, but performance of the futex syscall is not what's going to make the difference for him.
No.
This is a very specialized system call that you do use on machines where you care about performance a lot, on large workloads. We're not caring about the workloads on 32-bit machines that this system call is meant for.
Right.
Well, this particular, the weight vector, is meant for wine and proton.
Yes, exactly. And there is a lot of 32-bit Windows applications and Windows games that runs on Linux. So yeah, this.
But seriously, if you copy kilobyte more of cache hop memory or not, it really doesn't matter.
Okay.
And how often would you even have like a fully populated array? Like usually I'd expect you'd have a couple of things in there, and you can have the corner case where you have 128, but that's going to be the really rare case.
Well, so what does wine do? I think Windows NT or something has 64 for the multiple weight thing, and then we did Vutex for 128 just cause.
Yes, the maximum for Windows is 64, and I actually don't remember how we did get in 128.
I think for the wine implementation we had 64 and we had to use some internal things, so the next somebody just wrapped it up for the next power of 2. But we need 64 to serve that interface.
Yeah.
Yeah, so the worst case of 128 long vector doesn't even happen on the expected workloads. It's just 64 and a few.
Yes, you're right.
So yeah, let's just keep the code as is, and 32-bit will hopefully eventually die and go away, and then nobody cares.
Okay, so one question you shared. The struct on this slide here, it works great, right?
Yeah.
Okay, cool. All right, so actually this is how the interface would look like, right? Oh, and
Thomas
plus
wants a clock ID.
Clock ID. Yeah. Plus the clock ID argument, but the rest is fine, right? Or do someone want to give more feedback on the interface, or can we move for the next part? Okay, so I'll move on. So thanks everyone about giving the feedbacks on the weight on multiple, and I will send actually, okay, I need to add the argument. I will take your tree, Peter, and add the argument stuff and resend to the mailing list. And this is the interface for weight on multiple. But in the future, we will also want to add more the other syscalls to support weight and wake using 64 arguments. And this is how the weight and wake system calls look like. I don't think we have anything to change here. The only thing that we need to clock ID, yes, exactly, the clock ID. And yes, if someone wants to give some feedback, but I think this is very simple part. So for the flags, we'll have the private flag as usual. The clock spec we won't have anymore. We'll have a argument for that, and we have the for size that we won't support. So you have the flag for each waiter, and this is where things get complicated again. So we want to have NUMA awareness on Vutex, and right now the current implementation have a single global hash table, but with Vutex NUMA we will have one table per NUMA node. And how do you specify which node do you want to operate on? So one suggestion a long time ago on the mailing list was to use a struct. So instead of using this here on void user address, instead of passing the address of the Vutex that you want to wait on, you send this struct. So the first part is indeed the Vutex word, and the second part is what called Vutex, the hint, that is like the node ID where you want to operate on. And so the hint could be 0 until the max NUMA node, or if you send -1, you want to operate on your current node. So feedbacks about that? This seems reliable. Do you have NUMA people around here?
I don't think that's really workable. So for one, making user point to something else than the actual Vutex value is just introducing more code and more overhead. It's not worth it. So the question is, can we have enough room in the flags to actually hold the NUMA node?
No, you need storage. So the problem is when you do a wake from a different CPU or different node than you did wait on, how are you going to find the actual hash bucket?
Peter, I was coming to that. That's the next thing. I mean, Sebastian and I looked into that years ago, and we actually posted patches where you had to register your Futex ahead of time. That works, because otherwise we won't find it anymore. Or you have to, in the worst case, if it's not on the local node, you have to walk the hash of the other nodes as well until you find it, and that's going to be horrible in terms of performance.
Yeah, I know, been there, done that.
Yeah, so I mean the thing with Sebastian and I did back then worked perfectly fine. It's really performant and it's really nice. The only hassle is that people hated the notion of having to register the Futex in upfront.
Yeah, because a lot of people don't know what node they're on or what node they're going to be staying on, especially with stuff like the NUMA balancing. That might change over time.
Yes, I mean that's true. I mean it's not an, I don't know.
So and in that regard, adding user storage, I mean it's just extending the Futex value. You just store wherever you put the bucket in, and then on wake up you're just going to look at that one node, and then if you find it, good. If you don't, also good.
Yeah, but I mean so what you lose that way is if you let user point at Futex 32 NUMA, you restrict that NUMA add-on to 32-bit values instead of and you basically take it away for 64-bit values, which some of the glibc people really want to have.
And of course, if you specify in the previous slide a NUMA 64, then it will be a Futex 64 NUMA structure with two 64-bit words.
Okay.
I feel very
well. You don't care.
I know. I figured I'd do it anyway.
Well, because we had to wait for Peter to get online, didn't we say we're going to delay it? Let it go.
We already delayed it.
Oh, did you? I had a phone call and I had to take it, so I missed the last 5 minutes.
So Peter, if we denote the availability of a NUMA hint in flags, then this becomes an orthogonal problem, right?
So yeah, that was the idea. So if you have this extra word in user space, you add the flag, and that basically says the user space value is double what you expect it to, and the kernel can write whatever it wants in there.
Right. Yeah. Yeah, that makes sense. I'm fine with that. So we keep that in mind, but we do not implement it right away because that's an orthogonal problem and needs a lot of thought.
Okay.
Correct.
So for the sake of the poor note takers, do we have any conclusion on the NUMA-oriented Futex weight solution? I mean, I heard a lot go back and forth. The question is, we have firm conclusions, or is it just, well, we need to look at this more?
We'll need to look at it more. We have ideas, but we have to actually look at them in more details because there's quite some interesting questions open. So there's no final conclusion. But the final conclusion is that we think it is an orthogonal problem and we can solve it with an extra flag. and therefore we don't need to implement it right away.
Right. So also we need buy-in from the glibc people or whoever is actually wanting to use this, because there's more than glibc. I think some JVMs also use Vutex raw, and I know DB2 is.
Quite some databases use the raws install.
Yeah, exactly.
And other crap.
Of course.
Okay, so I think that's it for Futex 2 this year at least. And thank you everyone for the feedbacks. Thank you, Thomas, Peter. And then yeah, that's it for me today. Thank you everyone.
So we'll do a 7 minutes pause, and we'll be back in 7 minutes. Yeah, that's it. You guys know how to make jokes. I'm tired.
How
By the
long?
way, Daniel, you're kind of hard to hear. I don't know if you could raise your mic or mic close to
It's
your
going to
mouth.
be back when?
Let's do a 6 minutes pause, and we'll be back in the 15 minute.
50, I guess he's saying.
Yeah.
Yeah.
I will talk
10 of the
to
hour.
you. Yes, yes.
Okay.
John, are you ready?
Yes, I am ready.
I will pass the comment.
Okay, let me just turn this. Okay, so I'll go ahead and start.
Okay, you are really ready.
Yes, now I'm really ready. Okay, so I'm just here to talk about the current status of print K, and a lot of people ask the question, why is print K even related to real time? Because it's not something you typically think of as real time. So just to quickly recap, the reason why print K is such an issue is that when someone calls the print K function, you may print the line that you want to print actually out to the console. You may print no lines. You may end up printing like 1,000 lines that are backlog. It depends on the situation. So basically, it's totally non-deterministic how long this print K call could take. And of course, the consoles we know can be really slow. Serial consoles, for example, with low baud rates could really slow down that print K call. And of course, print K is allowed to be called anywhere. So, you know, often it is called in inconvenient contexts. For example, preemption is disabled, and that's not okay for real time, obviously, that we print out 1,000 messages to serial while preemption is disabled. And so this is why it's for preempt RT, this is a particular problem that we have to deal with. And you see down here that, you know, we could just avoid printing from time-sensitive context. That is the workaround we used in the 4. Kernels, for example, the preempt RT kernels. If you look in like 4.19, you'll see that when it's time to print, we check, are we preemptible, are interrupts enabled? Okay, then we will actually do the printing, right? So that's one solution. But then you have to wait for someone who, you know, when someone's printing from an interrupt context or something, then nothing gets printed, right? So then you have to hope that at some point someone comes along that's preemptible so that the message actually shows up, right? So that's not really a solution, and we need to find a correct solution for this. So we made the main decision, basically 2 big changes that we just wanted to change fundamentally with print K. The first, and they're about decoupling the print K callers from the printing, right? So we want, it's okay to call print K wherever, we just don't want that caller to be responsible for actually pushing it out to the consoles, right? And this is actually 2 main components that are responsible for that. So the first one is that we have a ring buffer, or the print K buffer, the D-message buffer, that is able to store messages from any context. Doesn't matter if it's NMI or in scheduler context, whatever. And we actually have that done now. With 5.15, you know, we see that we introduced a complete new, completely from scratch, lockless ring buffer, multi-reader, multi-writer, variable length, lockless ring buffer. All the crash tools were updated. We had to re-implement the log continuous message so that we could support doing continuous messages from NMI context. The log buff lock was removed in 5.12. Basically, these were the training wheels. They were left on even though we had a lockless buffer, but with 5.12, we actually pulled those training wheels off so that it was truly lockless. And with 5.15, we also removed the safe buffers. So now if you're in NMI context and you call print K, that's really going directly into the buffer, directly into the real D-message buffer, right? So this is a great, so fundamental position that we want it to be in. It does not matter where you are in the kernel. You could be, you know, in some sort of strange RCU callback, or you can be in the scheduler code, and you can really do print Ks, and they're just going locklessly now into this ring buffer. But that's just the first part, and that was the fundament that we now have as of 5.15. It's now totally in there. So, and that was mostly a technical feat to figure out how to implement the ring buffer and how to get it in without anybody noticing. So this is something that's taken about a year now, and now it's in there. The second thing we want to do is we want to, you know, because even though we're doing this lockless printing, this lockless writing to the ring buffer, we're still printing in the context from the caller, right? So we haven't decoupled yet. We've just prepared for that. So the second stage is we actually want to have separate dedicated kernel threads that actually do the printing. And if we can get to that stage, then print K is truly lockless. It can be called from anywhere, and we don't have to worry about context or anything for calling print K, right? So maybe even things like trace print K won't be as interesting anymore because you can actually use print K to debug just about anything. Now, this is the component that's not mainline yet. And the reason why it's not so simple is, obviously if you're just creating the kernel threads for the printers, that in itself is easy. And most of the printing would work just fine. But there are situations where the K thread cannot print. For example, when I'm shutting down the system, there's going to be a point where the CPUs go offline and the threads aren't there anymore. And now you have these final messages, ACPI, power down, or whatever, there are these final messages that come. They wouldn't show up, right? So, K threads can't help us there. Or for example, if you have early print K turned on, early print K will print out everything immediately, but as soon as a regular console registers, print K stops, deregisters, and a normal console takes over. However, at that point, we don't have kernel threads yet. So it means you would have you'd see the early print K, and then you'd have maybe a half a second pause before all the rest of the printing continues, because we had that gap there where the kernel threads weren't there yet. Obviously, in the panic situation, when we're just crashing in some situation, we can't rely on the kernel threads to put anything out. And then also for kernel debugging with KGDB, that's also something where we cannot rely on the kernel threads because all of the CPUs are quiesced. So the idea going forward here is that we would kind of use this method that we're using until now, so that the print K callers are actually the one pushing them out, that we will actually use that for these windows where we're not in panic situation, for example, and when we're shutting down, then we're going to go ahead and allow the print K callers to push out the messages. For real time, that's not a good thing, because we will have situations where preemption is disabled, but the idea is we're shutting down the system, and so perhaps we can deal with that, right? And the other window is between this early print K until K threads are there, right? So that's also a situation where we don't expect our kernel to be performing real time yet. So that's also a situation where we can go ahead and allow the print K callers to push the messages directly out, right? So just in those end and beginning situations. What we're also having there is we're introducing a new function called PR flush, and PR flush is it's a sleepable function, and this function can be called by anyone if they really want to make sure that all the messages that have gone into the buffer they're actually flushed out to all the consoles. And we can do this in the PR flush context, right? So the person who's the task that's calling PR flush, that's the task that's also going to push out all of the remaining issues. PR flush is a might sleep function, so that's totally okay that we can do that there. Now, for the situation with panics, it's a little bit trickier because we don't want to use the interesting techniques that we're using right now, busting spin locks, ignoring spin locks, and just kind of trying for that. So what we're doing is we're introducing something called atomic consoles that are actually only activated in a panic situation. And actually, we'll probably, for the mainline, it might be probably renamed to panic consoles, because it really is only in this panic situation. And what these panic consoles or atomic consoles are is that they will locklessly just push out the data to the devices that support that. So for example, if it's a serial port, this is relatively easy to implement, locklessly pushing out the data. Now, atomic consoles, even though it's only in the panic situation, so they don't have to do so much worry about synchronization, they do have to worry about one case of synchronization, and that is what if we were pushing data out on the serial and we panicked in that moment, right? So we have the normal console drivers that were in the middle of doing something, and now we hit this panic situation. So we do need to have some way to synchronize the regular consoles with these atomic consoles, and for that we have something called the print K CPU lock, which is basically a CPU reentrant spin lock, which means within the same CPU, I can keep grabbing this lock. So if I was in a, you know, a preemptible context and then an interrupt comes, I'm allowed to grab that again. Maybe an NMI now comes, I'm also allowed to re-grab that. But all the other CPUs, if they try to grab this lock, they'll spin. So it's just to keep other CPUs out. It's not a real lock because I still, I'm not really synchronizing off this for the same CPU, right? Because, you know, there still could be these interrupt contexts. So I still have to implement atomic consoles lockless, but at least I don't have to worry about other CPUs coming into there. Now for the preempt RT patch, I actually implemented a separate call for this called write atomic. But later it was pointed out to me that KGDB actually also has a set of polling callbacks that work very similar. They're mostly lockless, and most of the serial devices support these. So I'm actually looking into, can I recycle that code, or can we build the atomic console stuff around that? And we'll, in the last slide, the next slide, I'll just kind of summarize that. Now for the topic of KGDB, this is also something very interesting because KGDB basically will quiesce all of the CPUs except for the one primary, so KGDB CPU, and all the other CPUs will just be spinning in NMI context, waiting for something to do. And the problem is you know, when the kernel's debugging itself. And so what we have to decide here is what's more important. Is it more important that if KGDB crashes, that we see a stack trace from KGDB, meaning that this atomic console infrastructure is underneath, is deeper, lower level than KGDB? Is that what we want to see? Or is it, do we want to be able to step through the atomic console code with KGDB, right? So I haven't been able to figure out how we could do both, and I don't think it's possible. We have to figure out, do we want to be able to step through atomic consoles, or do we want atomic consoles to be the fundamental level of the kernel so that if KGDB crashes, we have a nice stack trace there? So that's really what that's about, and I've had discussions which we see here with Daniel Thompson from Lenaro, who's really the primary maintainer, I would say, for KGDB and this work there. And his idea was, could we have, for example, KGDB take this CPU lock from another task that already has it, right? So let's say we have a situation where the CPU lock is taken from a CPU, and then the kernel hits a panic and we jump into KGDB. So now that task that was holding that CPU lock will jump into the NMI, will be interrupted into an NMI context that's now spinning, but it's holding the CPU lock, right? So if it's holding the CPU lock, then no other CPU can do atomic printing, right? And so now my primary KGDB master is not able to do atomic printing because it doesn't have the lock, this CPU lock. And so the one idea from Daniel Thompson was, can we transfer that ownership? And generally, when you're talking about locks, this kind of defies the concept of lock, but I haven't thrown this idea out because the CPU lock is not a real lock. The primary purpose of the CPU lock is to prevent other CPUs from getting into there simultaneously. But in KGDB, we've quiesced all the other CPUs. So transferring that now to the KGDB primary might actually make sense, so that the primary KGDB is now also there. It's also making sure that no other CPUs can get in there because it's the only one that's running, right? Now, of course, if we're going to do that, if control is ever restored back to that original owner, obviously it has to be transferred back before that quiesce is released so that it can continue. But this is something that I'm still looking into how we would like to do it.
Might be interesting to consider changing the name of what you're now calling a console lock, because it's really not a lock, and that kind of drags along a whole bunch of baggage with it.
I totally agree. I'm really bad at naming. If someone has a better name for that thing,
I don't have a good suggestion for you either. I suck at that's why I'm not in marketing. But
CPU synchronizer.
Yeah, I mean, probably should be something catchy there, Stephen. But you know, which CPU synchronizer or not? Okay, I could go with it.
And the thing is this isn't new in the kernel. Actually, we've had these before, and I'm consolidating them all, so because you actually, if you have multiple in the system, it's a deadlock danger there. And in all of them that we've had, there was never comments saying what they were. There was no names that made sense, right? So yeah, but yeah, I agree that CPU lock is a bad name, just because that word lock is misleading, especially if developers of atomic consoles, they will make use of that thing to help them synchronize, right? So if they think that it's a lock, then they might be having issues. It's not a lock. It's just preventing simultaneous access to the section, for example. Yeah, so that's a good idea. I'm open for names. What was it, CPU sync or something like this? That's I'll take it, right?
Yeah, CPU sync or whatever. You put that in the notes.
So this last slide here is basically showing on the left-hand side, you see the way Preempt RT has implemented these final issues right now, and what I may have to change for mainline acceptance. So for example, currently we're using also atomic consoles in this window here because we want in Preempt RT, the idea was it also looks nice when early print K immediately hands over to, continues to print. You don't have this gap of, we don't lose messages, but there's just a time where nothing is printed while we're waiting for those K threads. So currently Preempt RT is using the atomic consoles for that. For mainline, that's not going to be acceptable. The main argument from the print K maintainer is we can't assume that people have atomic consoles, right? And so he wants there to be continual printing in that case. So the way it'll probably end up being is that, like I mentioned in the slide before, we'll use the way we're using now, where the print K caller is the one that'll do the actual printing. We can't do that for RT, right? Because if there's interrupts and things that are happening there, we can't print. So that means in RT, if you turn on RT, you'll probably will see a gap of no printing. Unless we want to do it like I've implemented now for RT and say, these are atomic consoles, they can be used anytime, not just at the panic situation, and we use them there. So this is a behavior change that in particular the Preempt RT people will notice, that now all of a sudden, they see the early print K and then there's a half a second of nothing, and then it'll suddenly continue when the K threads are there. I'm not sure if that's acceptable. It'll go into mainline well, but I'm not sure if for the Preempt RT people that's acceptable. Also, PR flush in Preempt RT currently just simply waits, right? So it's just waiting for those threads to finish printing. But if we say, no, we want to allow print, there's going to be situations where print K callers are allowed to print. I named them, like when we start up and when we're closing down. Then we can just change PR flush to actually do the printing, which is what I actually prefer, and that's the way it's going to go in mainline. That's the way it makes sense. It's more effective than what's currently in Preempt RT right now. For non-panic termination, PR flush is currently being called, but like I said, in the Preempt RT, it's just now waiting and hoping that the kernel threads are printing. On the non-panic situation, actually, that works pretty good. You do see these final messages at the end, but for mainline, I'll also be changing it so that in that moment when we are going into the shutdown, any print Ks that happen there are also allowed to call this. Again, for Preempt RT, we're not allowed to do that, right? Because there will be situations. I mean, we can do some context checking. We can check if we're in an IRQ and if preemptible, so that we could try to do it in RT as well. But generally speaking, that's not as reliable with Preempt RT. So there's a risk there that, maybe with Preempt RT, you don't see certain messages, right? So these are the things that I'm kind of the battling to get it into mainline, because mainline wants the behavior to be exactly as it has been. And for Preempt RT, basically, but I've been using these atomic consoles to kind of push everything out. Unfortunately, the atomic console is only available on the 8250 UART. So if you have anything else, then basically you don't see any atomic consoles in Preempt RT right now. Another thing that I did is in the panic situation, Preempt RT currently only uses atomic consoles for printing out those dumps. So for example, in Preempt RT right now, if you don't have an 8250, you aren't going to see backtraces, right? Because there's just no atomic consoles that are available for you. And of course, the idea is we want to implement atomic consoles for everything, but the question is, do we have to wait for that before we get it mainline, right? So this idea of only using atomic consoles for printing the panic, I'm going to get away from that. And the idea now for my next version is that if atomic consoles are available, it'll use them just for that stack trace, right? When we go into this panic, we do the back trace, and it will try to use atomic consoles for that full back trace. And then it'll fall back to what we have today, which is bus spin locks and just try whatever. So it's the best effort to try to get whatever's out there, right? So for people that don't have atomic consoles, the behavior will be the same as today. But hopefully, if you're dealing with a real-time system, hopefully you have an atomic console available, and then you have that guarantee. And to continue on the atomic console topic, these polling APIs are really available for a lot of the consoles. So I'm now also debating, rather than having a new like write atomic callback, maybe I could just have a generic write atomic function that is making use of these polling APIs that already exist. Now I've looked in, for example, the 8250. The 8250 polling API does actually have scenarios where it can take a spin lock, and that's not going to be allowed. So I might have to, play around with some of these polling APIs, but that might be a better chance or a better shot into mainline rather than introducing a whole nother function that everyone now has to implement. I'm not really sure. I know, and there's a lot of subsystems where they have these callback functions, and most of the people just map the callback functions to a generic function, right? So we could have that, so that if the polling API is programmed the way it needs to be, then people can just map it to the generic function. Something that I'm just currently thinking about for the next version. And the last two things are about KGDB. And currently the way it is in preempt RT is if you're holding this CPU sync object and you jump into KGDB, so you're jumping into this spinning NMI context. Currently in preempt RT, I've implemented that you see that you're holding this. And so what it does is it'll exit out the NMI context, allow the stack to do whatever it wanted to do, and when we're releasing that CPU sync object, it'll re-trigger the NMI to go back into KGDB. The idea being we don't want any of these quiesced CPUs to be holding that CPU lock or that CPU sync object, right? So that's the way I've implemented there. But Daniel Thompson says that he's not convinced that that will work in lots of situations. KGDB has a lot of tricky features where you can switch which CPU is the KGDB primary CPU. And so he's not convinced that that should work, although I'm not really understanding, because if the CPU lock, if no one's holding the CPU lock or the CPU sync object, then who cares if we're switching back and forth, right? But I have to look at it in detail and really consider this idea of transferring ownership. It's just about supporting these KGDB features where you can just command different CPUs or allow others to take over. Also, KGDB has that feature that anything you do, for example, in KGDB or KDB, is mirrored on all the other consoles. So if I type in a command or I want to see a backtrace or anything, all the other consoles on the system mirror that output and actually even the input that I type. And it does it with a really, really horrible hack of setting oops in progress and pretending like we're crashing to kind of trick these different console drivers to print, right? And we really want to get away from that. And so the preempt RT is using the atomic consoles for this as well. However, maybe that's another thing where we say, okay, the polling API, or somehow I want to get away from this dirty trick of tricking consoles to thinking we're crashing or things like that. So these are just little things that I just still need to clean up there. Question, Clark, or comment?
Helps to unmute. So I wanted to make sure I understood the concept, the constraints you have on atomic consoles right now. And it sounded to me like the only actual atomic console we have on either preempt RT or mainline is an actual physical UART, 650 UART. Is that correct, or did I scramble that some?
So Mainline has these polling APIs. Mainline actually has, for almost all of the consoles, they have a polling API available. And the polling API is what KGDB uses, which is basically lockless. However, like I said, KGDB uses tricks to kind of sets oops in progress, which might help. I haven't looked at all of them, but most of them seem to be pretty lockless, where they're just, you know, putting a byte in the TX FIFO and waiting till the TX FIFO is empty, and that's pretty much how all of them have implemented. But it's just the UART. So, you know, the net console and the graphic consoles are not implementing the KGDB, the polling APIs.
We don't have that on Preempt RT right now. We don't have those polling APIs, is what you're saying.
They're also available. They're also available, but I'm not using them, right? So I only implemented the 8250, and I just have a new callback called write atomic, and you just give it a string and it just does it. And so I was looking at my implementation of write atomic and comparing it with the 8250 polling API that it also implemented, and there are similarities. But for example, they possibly could take a spin lock, and that's absolutely unacceptable for the atomic console.
Yeah, I was just confused. Situation normal.
Okay. Any other comments or questions? So I actually presented a version 1 LKML a couple of weeks ago that did most of this groundwork, but a lot of these things that now you see on the right hand side, these changes are just things that came back from Peter. He's a great maintainer from PrintK. He's, you know, if you look at the things I'm doing here, is a lot of hard line. Basically, I was like, I don't care if you don't have atomic consoles, you don't see it. You know, I was just basically throwing out a lot of stuff, which obviously is not going to be acceptable for mainline. So, you know, we're working together to try to find a middle ground. My main concern is that, you know, for the Preempt RT experience, you know, when it's booting, you'll have a pause that you don't see messages. Obviously, you know, if it crashes, you will, because the atomic console. But you know, you will have the pauses there, or when you're shutting down, I'm worried that you might not see those final ACPI power down messages or things like this. So, you know, that's the kind of things I'm kind of looking at right now. And the KGDB is also causing considerable headache, just because KGDB is extremely complex. It's used its own CPU sync objects, and you know, I just have to dig into that because it's really sensitive code. And you know, my method of just saying, hey, let's just make sure I don't hold that CPU lock, that was kind of an easy fix, but that may not also be good enough. So we have to see.
We got a question from Sebastian.
Sure.
John, regarding the atomic consoles, what's wrong actually with implementing it for the other drivers as well and making it somehow mandatory to have it?
You know, it's just work that needs to be done. So, you know, Peter is the PrintK maintainer. He's expressed he does not want to take things in the mainline that are having missing pieces. Right? He wants it to come into mainline ready to go. And so my concern with that approach is now we have to implement 60 atomic consoles before this code can be acceptable to mainline, which I would, you know, I guess that's a direction we could take as well. But I mean, that would probably, I mean, if I had help from other people, we could probably have enough manpower to get it done in a few months. But it's a lot of drivers, and you have to learn, you know, a lot of these serial drivers, even the 8250, it's not just a simple driver that you have to worry about. You do have to worry about interrupts and the enable interrupt register, and it's actually quite complex to do that lockless. You know, if you were to look at the Preempt RT patch on the 8250 atomic console implementation, it's not trivial, and I had to spend a lot of time to understand that hardware in detail so that I could do that. So now if we say, okay, I have 60 different UART chips, we have to understand them in the detail to understand, can we do lockless and how do we do that? And it's just a lot of effort. So
you don't think we could
trying to find a way around that.
You don't think we could convince Peter to allow us to phase it in one particular device at a time?
He's open for that, as long as it means that for people that don't have it, they have the experience that they have today, right? That's the key. They don't want this experience to change. And with the things that I've written here on the right-hand side, if we ignore all this, the atomic parts, these first three items, that'll allow people to have the exact same experience they have today, which is what we need. And then, maybe we can say, if you have an atomic console, your experience is even better. And then we just implement them one after the other, right?
I think Greg has something to say.
Right, go ahead.
Yeah, that's okay. We can't do it for all of them at once. Let's do the main one, the 8250, and then we can phase them in after that. It should not be a limiting factor.
Yeah.
Because there's no way some of these embedded crazy SoCs, you're ever going to get them all. If somebody, like Thomas said, we give them the option. If they want to do it, they can do it.
Yeah,
And
I'm just kind of browsing through.
Copy me explicitly, because I've been watching the patches go by, but I missed that Peter was complaining about that.
He's not complaining. It's a valid concern, right? And like I said, the way I implemented it in Preem RT, people without atomic consoles have a definite disadvantage, right? And he said that's not okay, and it was correct for him to say that, right? So
no, that's okay.
So we're just turning it around and saying, okay, let's make atomic consoles a plus if you have it, and if you don't have it, it's the same craziness we've had until now.
Okay,
right?
yeah, that's fair enough. Yes, if you want to do that way.
Right. So that's kind of how we're going about it.
But don't worry about getting all 60 consoles.
I think that's the right way to go. So we give them, so we try to, keep it halfway compatible with what we have now, with all the downsides, but we give them the option for a sane panic interface, and that's, I think, important for a lot of people anyway, because what we have right now, in 90% of the times, you're not getting what you want to see. So people should be easy to convince to actually implement that with their special knowledge of their hardware. So when we sat down 2 years ago with all the involved people and talked about this, then there was consensus in the room that even the graphics people wanted to have this dedicated interface so they really can act upon it and not say, which crystal ball should we use to figure out what's going on? I think that's the main advantage we're getting here.
And I would just like to point out, we don't have any real roadblocks, right? So we really have the mainline community behind us. Where I'm really curious what will happen is with these threads in general, because it will be a slight behavior change. Yeah, people, if you're using the preempt RT, you maybe already noticed it, that these messages come slightly delayed. If you have a machine that's very, very busy, those threads might not get as much chance to even be scheduled, right? So you might have to just decide you want, for certain consoles, you want to give them a real-time priority or something so that those messages can come out more immediate. But these are things that we've never had to deal with before, right?
No, I don't think it's a real problem, because most of the messages are really just noise, and people grab it via the message interface anyway. It goes into Syslack and whatever, and is analyzed. So the consoles themselves. If I look at the serial console, I always hate it. And the only thing reason why I have it on is because if the thing crashes, I want to see what's going on, and it's the most reliable we have today still in 2021. So no, it's not a problem of whether it gets delayed or not. People don't care. If you look at most installs, they have quiet on and hate it when you have actually warnings popping up during boot, so they want to have it nice and calm. So I don't think it's a real problem.
I agree. We'll see what the people say.
And of course, I don't know, do people still use Peter Zylstra's early print K hack that just turned everything into early print K when you want to see? It kills the latency in case there's a D message, but when you're debugging something.
I use it.
I used it 2 days ago, to be fair.
I was wondering, should we try to get that main line or just have an option to turn, like a command line option to say, screw it, this will kill latency, but command line option just, and accept his patches. I don't know.
It has a command line option. It's all nice and shiny. You say force early print K, and then this happens.
Yeah, the problem is that it's not actually a multi-CPU safe, SMP safe, right? So
It has the crummy CPU byte blocking thing on.
Yeah, it has. Peter implemented like the that CPU sync thing that we have, or that you have, or it's formally known as the CPU print K CPU lock. Peter has that in his, so it is SMP safe.
Okay.
Yeah, because without that, it's really unusable.
Yeah, I mean that would be simply implement, right? So as long as this is a debugging option, yeah, why not?
The interesting
Yeah,
thing is
I can send them again because I've been carrying it for years now.
Peter, if you have actually a console which allows or provides the atomic or panic or whatever we name it, right, then having this makes it even easier because it always goes straight through. So if we actually have a console like a 8250, which provides the atomic write callback, and then your option force early print K will just always write directly through. And
Correct, that's
not,
the feature.
pardon?
That's the feature.
Yes, but the thing is, once the console gains that callback, then it's actually capable of doing this force straight through thing. While today, forcing it on anything else than 8250, no. So I rather see that implemented on top of that interface.
Yeah, sure. I mean, I've been using it on pure serial ports because that's the only actual reliable output we have. But
yes, but the thing is, I mean, if we have what John is actually implementing right now, and then we get this extra callback on a particular console. At that moment, we just can have a command line option switch, force atomic writes on the console, which then obviously forces it only on those which have them and ignores all others. But then it's a core infrastructure property, and you gain support once the particular drivers gain support. Doing it the other way around, I think, is wrong.
Sure.
So you get it for free, almost.
All right, thanks guys for the feedback.
Nice job, John.
Yeah. So far, we have been having a nice discussion. It's really nice to see how productive it's been, this microconference. And now
Yeah, but
it's
now
our
we're
family.
going to get a roadmap, right?
Yeah, now we get the famous question and answers from Thomas Claxon, and he will present the roadmap. So the idea of this last slot is to make questions, hard questions to Thomas Klexner and see what he can. So do we have any questions about the printer tip to Thomas? It's your chance.
So wait, preempt RT is in the main line now, but does any architecture enable it?
No, because it's not completely in mainline. We have big chunks of it there. We have still a couple of things to fix and get merged, including Prinke.
We should probably push that patch for compile test, though.
Yeah, I have it in the pipeline of patches I'm going to send once this conferencing crap allows me.
Fair enough.
So we made good progress in this merge window, but we're not done yet.
Got two big chunks in. Lock them in. Those are two scary changes.
I was thinking if we should have at least one arc enable preempt RT. I'm thinking maybe user mode Linux.
Oh God, we never tried that.
So,
But
so
the thing is,
you'll be running real time as a demo. Is that right? Like Stouty?
Stephen, it won't work. I mean, there are essential pieces still missing, so it will colorfully explode. So what Peter and I were talking about is making it easier for actually compiling the RT artifacts on mainline. I have a patch which enables that for x86 by just adding the select or no actually not only for x86 in general, by saying if Arch supports or test compiler, whatever the config option is. I mean, if somebody compiles that thing and then boots the kernel, it's his problem. I don't care. But it allows at least compile testing.
There was an explicit bug in that patch, so if you try to boot it, you die instantly.
Yeah, no, not instantly. It dies. Once soft RQs are used, then it dies.
Well, or maybe what you should do is just make it so it never goes to user space. Boots all the way up to.
It won't reach user space. It panics.
Right. So basically, have it just if you enable this, not it could boot all the so you could test the boot process of it, all the way up to the point where it would call init instead of calling init. It just.
No, you can't.
Panics.
Okay.
I mean, it either lock. It will panic because I have panic in there, an explicit and early on, and other than that, it will just lock up. Or if you have debug options, some debug options enabled, you're going to be drowned in debug messages. So no, no, it's not going to work. I mean, we have to get the other pieces in. It's not that big anymore. So the essentials we have to bring in. It's about 100 patches and it's 2,000 lines added and 1,000 lines deleted or something like that. So it's rather tiny now.
So can I ask the question? I mean, I know print K is an issue, but among the other things outside of print K, if you were to allow it to boot, is it just the fact that we have places where it's going to crash normally, or is it, or like those other places that we need to fix up, or is it just the fact that we could have unbounded latency?
No, it's probably just going. I haven't tried, but I expect it to just spectacularly deadlock somewhere.
Okay.
So I have tried because I couldn't be bothered to, but shouldn't be. You can figure it out what happens.
Yeah, I guess all you have to do is just add the one line in the architecture that it supports it and try booting it and see what happens.
Right. But you can keep the pieces.
Yep. I mean, if you modified the kernel, it's your fault.
Yep.
Well, it might be interesting to try it.
So what's your plan for the next merge window, Thomas? No, I know you got some print case stuff, and I seem to recall seeing that you were fiddling with file system namespaces.
Yes, yeah. That's my main headache at the moment. I mean, we have the CPU chill hack still there, but
oh yeah,
it's not really pretty. On the other hand, the KVM people actually say, "Oh, we want to have CPU chill instead of CPU relax." Because one of the things with the trilog loops is where we have a CPU to relax in there. If the vCPU, which is holding the lock, is actually scheduled out, then you spend the whole time slice in order to do trilog CPU relax, trilog CPU relax. Yeah, it's not pretty either. So yeah, but that the namespace, file system namespace stuff is pretty interesting. Let me phrase it that way. It's really hard to understand what's going on there. So I don't know whether but that's at the moment the least of my worries. We have a couple of things to fix up in MM still, but that's not big pieces. But we need better solutions than we have now, and we have a couple of smaller networking issues. It's nothing big. It's just, I mean, some of the changes you really want to sell proper, and at times I sit there and have a 5-liner change, and then spend half a day writing a changelog in order to make it palatable for the respective maintainers. That's the main thing now, because yeah, you change 5 lines in this so important performance sensitive code, and then you argue for half a day whether this is actually costing you half a CPU cycle or not, because it's so carefully thought out or not. I mean, that's reality. It's been that forever.
So is it mostly subsystem fix-ups that you guys are, subsystem and driver fix-ups, that's a big concern now?
So yeah, it's MM, it's FS. No, yeah, FS is only. Yeah, we still have to sell the Dcache changes, but I think they should be not a big point of discussion, because we can abstract them completely away. Linus will hate them, but he will accept them, I think, as long as they don't or really restricted to preempt RT, because what we do there is basically change the wait queue to an S wait queue, which is suboptimal, but it actually works. The other things is networking, where I really have to look at how we sell that to the network people. Ideally, we find an issue with their current implementation, which is not that easy in all cases. The rest is small adjustments here and there, left and right. A couple of things have been merged already in the various maintainer trees. Yeah, we're walking through it, and I mean, then we have this RCU problem lurking, what Valentin found out, and I looked at the patches we had; they were broken, and then I looked at the latest version and figured out, no, this doesn't look right. So actually, I decoded what can be done without introducing something. And no, Mark, he shouldn't post the traceback. This is going to be this takes us until tomorrow until he's done. So it's just the small bits and pieces which need to be addressed right now in the right way. But I don't think, except for technically, we have print pay, which is a big pile, and we have file system namespace, which is mind-boggling. But than that, it's mostly just spend an awful lot of time staring at it, whether there might be a more elegant solution, and if not, come up with a reasonable changelog in order to convince the maintainer to take it. Yeah. Any other questions? What's that?
I do have a question. If it is, it's not exactly preempt RT, but soft RQ's latencies are an issue even without using preempt RT. I'm just wondering if any of the work done will benefit systems that don't use preempt RT. I know that the problem is like in Android, there are audio glitches because of soft RQs, networking one particularly.
Soft IQs are a permanent cause of trouble.
Yeah, so Peter, this suggests a solution which I'm trying to work with Google on, but I just wondering, like, I thought in my head the nicest way is threaded RQs, which I think they are preempt RT, protected by preempt RT only. But generally, I think the improvements for these latencies could benefit users outside the preempt RT, and that's my main question.
Yeah, but that's hard to achieve outside of a preempt RT kernel because we radically change the preemptibility of the kernel in favor of real-time workloads, which is the opposite of what the performance people want to do. Actually, hog the CPU as much as they can. So it's the trade-off. It's the trade-off between deterministic behavior and throughput, and the other people care about throughput versus the trade-off of being not as deterministic. But there are definitely areas where those overlap or collide, so there might be some interesting outcome in the future. So we saw interesting developments in networking recently, where people are moving to task-driven networking, which is less horrible than soft IRQs, and they have some good results with that. So this will take a time because the network stack is fundamentally based on the soft IRQ assumption today. That might change over time, but that's going to take a long time.
So is that the threaded NAPI stuff you're talking about?
It's
because now they instead of one software queue, they want to have it basically K threads, and they could run on multiple CPUs to process all these interrupts, I think.
Right. Yes. And one of their goals is actually to eliminate most of the software queue disable areas in those processing threads.
Okay.
So that these threads actually get back under scheduler control, which is the main problem of soft IRQs today.
Right.
Because,
so what's
soft
Peter suggesting?
Soft IRQs interrupt or context stealing in a non-RT kernel. So they run in the context of the currently interrupted task, and then they just take as much time as they want. We have some heuristic limits into it, where we, if the software queue processing takes too long, we just schedule K-software QD for the next round, which works or not.
Yeah,
but this makes it, this removes it all from scheduler control, and that's actually turns out to be bad even on non-RT workloads, because we really want to have more stuff controlled by the scheduler and not by the preference of some programmer.
Yeah, so the limit is useful, but if you have one software queue that's taking too long, the current limit, even when you try to improve it, there is no way. I mean, it has to return for you to be able to.
It's an endless bit. So that's just everything people do to improve the situation is just band-aid. It can't fix all the things. So the only real solution is to move work out of software queue context, get rid of the software queue disabling limitations, which means which includes preempt disable on an RT kernel, and then you actually give control back to the scheduler, which can do useful things or decide to run something else if it's necessary. So there's a question on the chat. Is there an appetite for restoring K-software QD? Yes, no, yes. Actually,
No, that's K-timer soft-D, not IRQD.
Yes. We surely could bring that back, but the problem is right now we have to concentrate on getting the current stuff upstream, and then work from here and bring back optimizations over time. I mean, I'm happy to carry a patch or patches which fit on top of the RT series, but my bandwidth actually at the moment is too limited to even think about it. I mean, it's not really a bandwidth limitation, it's also a budget limitation, which limits the bandwidth. Any other?
Don't be shy.
That's
Looks like
relaxing.
Masami's writing something, I guess.
Okay, that takes a long time. He gave up. Oh no, Mark is typing.
I guess if everybody starts typing something and just keeps and quits, we'll all be here staring at the chat.
Come on, people. There are other questions.
That wasn't an invite.
Yeah, it's just a jumping, but yeah. So the what we need for the preempt RT is in our mainline is just enabling that.
I mean, so we have to enable it per architecture.
Yeah.
So we have constraints on the architectures which are not that big anymore. So the x86 related patches, or I think we have 4 or 5, and it's something like 100 lines. So this is not really big anymore. If I go back in the early days of RT history, there were a lot of patches affecting the architecture code, but this was mainly because we did not. A lot of the things were actually needlessly duplicated in the architectures, like timekeeping, timers, interrupt subsystems, and all these kind of things. And we are slowly moving, or most of these things have been solved. We recently did the generic entry code stuff, which we recommend for preempt or T-enabled architectures, because then we have one place to modify and not five. Going with these things to actually think about consolidating needlessly duplicated code makes it easier. And yes, there was a related question from Mark, whether we have to be afraid of architecture codes in the future, which comes in. I don't think there's much of the architecture code which is really affecting RT anymore. So I mean, the low level access is to the hardware have to be protected by either spin locks or disabling interrupts or whatever. Anyway, so there's no way around that. But those accesses are usually very short critical, so it's not really a threat to RT anymore. And people have become smarter over time, not to say lock world, do tons of shit for 5 seconds and then unlock world. I mean, those times are gone. So people got more sensitive to that, and I'm not afraid of it. I mean, if shit breaks, we fix it. Everybody's typing, nobody is asking questions. Stephen, how did you make it link? Without changes?
Oh, I just went through. I did change it. I forced the config, but it looks like I booted it, but it still fell back to preempt, I think. At least it says it's preempt.
Actually, it can't even link when you enable it.
I was hoping to get some sort of error on there, but at least on the compile error. Why did it? Let me check the menu config again, because I guess it.
Moore. So you say, when can we confidently say we can install this in a critical system? I mean, define critical. I don't know. There's a huge amount of RT instances out there, and if you define it, if it fails, we all die. Okay, no, never. I mean, it's not going to work. I mean, you can't validate such a complex beast.
Is there any software that we trust that much?
No. I mean, safety is a complex beast, and it's not only about software; it's also about the hardware. There's a lot more constraints, and you can really construct. Even, I mean, people have built rail safety systems with diverse systems in Avoda 20 years ago. One running Linux on a PowerPC and the other running Windows 95 on an x86. You can make a safety certified system out of this if you do it right, because it actually make the operating systems go into a black box, which is not relevant to the actual safety problem at hand, because you have an external voter which actually decides to put shit into a safe state, which is okay in a lot of cases where you look at safety. If you think about self-driving cars, there's a small problem here. What's the safe state? It's not really well defined with moving cars on a highway. So it's really a complex problem. And I don't know what the people do in who actually use Linux for rocket control, how much safety net they have. I don't know. But a rocket might have the whole thing stay in safe state as well, make it explode.
I'm not convinced they use it for actually that purpose. Maybe they use it to process images and this kind of stuff, Linux, but to use it as
No,
I think they still use RTOS.
SpaceX has it in the rocket control.
In the rocket control.
Yeah, I mean, it's just a matter how you design it. If you have a properly designed redundant system, it's not a big deal. I mean,
I think it's not critically safe, this one, because I thought at least for medical you will need to pass certain certification. Maybe the rocket doesn't need to pass.
No, actually, you can. I mean, you really can get SIL 4 certification if you do it right with just Windows 95 and a box standard to Linux to something Linux kernel. It's fun, but you have to do it in the right way, and you have to the right voting and decision mechanisms around those thingies, which actually have to be certifiable, and that's a very, very common approach, because the less complex the actual decision making and the safety relevant part are, the more freedom you have on the other side. But that's really application dependent. As I said, there's a way easier decision to make what's the safe state of a train than what's the safe state of a car moving at 100 kilometers per hour on a highway, together with 500 other cars and trucks and whatever. So that's just a matter of complexity, and so if you have a well-defined safe state, your decision logic can be very, very small and easy to certify, and it can circumvent all the stupid certification for the OS completely, because you can look at it as a black box which has an output.
They don't have to certify the code itself.
No, no. You have to certify the decision logic, which says 2 out of, depending on your complexity, 2 out of 2, 2 out of 3, 3 out of 4 agree, and that's okay. If they don't agree, I have this knob which puts it into a safe state. That's fine, as long as you have a well-defined safe state.
There will be a talk about this tomorrow, actually, where Gabriele Paolone and I talk about the approach that we are thinking it would be good for Linux. Because there are some ISO rules that say we could use some software testing it as a black box, but it seems that for the automotive case, Linux is too complex to be tested on that regard. And there are some discussions about it in the Lisa front. And tomorrow, actually, we'll have a talk in the referee track where Gabriele Paolone and I will show what we are thinking to do, or what we think, or what the community thinks is a good direction for the Linux. But yes, it's always a balance of what you turn into a black box. If it's entire Linux, it's part of Linux, and test integrations. But it's very dependent on the system you aim to certify. And cars are more complex than the system like, probably great, more complex than system like rockets or trains where you have a more controlled environment. But yeah, it is an open issue for the entire community. And
Glenn, community blast RT-config template. What's your action? It's also very, very application dependent what you really want to have and what features you need and what features you want to avoid. It depends on what latency requirements. So real time is really, it's a design problem. It's not necessarily yes, it becomes a configuration problem at the end, but in the first place, it's a design problem because you have to understand what you're trying to achieve. And then you have to define your constraints and group here. So by real-time control loop, which has to have a period of 1 second and has a maximum latency of, let's say, 100 milliseconds, is still real-time if the outcome is critical. But it's very relaxed environment than somebody who's trying to do a 1 kilohertz control loop on something. There is no real, I mean, there only can be recommendations on what might cause latencies if you really go for the 2-digit microseconds latency range, but there's no real recipe for that because it's real-time system have to be designed from ground up. Like safety, you can say, okay, I throw a safety OS at my problem and everything is safe. It doesn't work. For security, you have to design security. I mean, it falls all in the same ballpark. And our problems get more complex. So there should be way more time spent on design than on, and then if you have design and have your requirements well defined, then usually the configuration will fall out of it.
Thomas, sorry, I asked it on chat. Are you thinking about some documentation or some sort of help to kernel developers to feel more at ease in this world of Linux kernel development with RT in mind? Because we have lots of caveats with contexts and taking locks in sleeping contexts and all that stuff. So are you guys thinking about something to help people to?
We wrote quite some extensive documentation on the locking constraints, explain the differences between RT and non-RT. And yes, we should expand on the documentation. So help is welcome, patches welcome.
Thank you. Yes, I was asking that because the current documentation is really interesting, the lock types and the lock in preemptible context, but maybe something else. Yeah, thank you.
Yeah.
So, unfortunately, our time is up, and we should close the bar. Anyway, it seems that it was the most productive micro conference we had in the last years, at least in the real time realm. And I would like to say thanks to everybody who participated and engaged on discussions. I'm already having some nice feedback for people that participated, like for the first time. And it seems that we have a real community around here. And yeah, thank you all. Mark, any more?
Thanks for running it, Daniel. I think you did a really good job.
Thank you.
My pleasure. And that's it. We love you all and see you tomorrow.
See you tomorrow.
Bye-bye.
What?
And Daniel, you could save the notes. I already did too. But I gotta go through and save them
Okay.
for all the MCs this time, since we forgot to do that
Yes.
last time.
Yes, I already saved a copy as well. And thank you for everybody who took notes. It's very hard and I really appreciate your help.
Thanks, everyone. Don't end the meeting.
Yeah.
Daniel, you got the notes?
Yes.
How did you copy paste it, or is there like a way to download it properly?
I copy pasted.
You click, no, you could, okay, if you're in the shared notes, you see the two arrows up on top?
Ah.
Click on that, and you can export it as HTML, plain text, Microsoft Word, PDF, or even ODF.
So we want it as Microsoft Word?
Yeah, you could do it. I did it in plain text, HTML, and PDF.
Where is the RST option?
Well, you could, yeah, the LaTeX option, that'd probably be better. And there's Etherpad, I don't even know what format that is.
Ah. And it has a really nice name. Is that like just a Git commit ID?
The what?
The name of the file. Is that just the Git commit ID?
No, I don't think it's a Git commit. I just think it's just some hash that they use. Okay, so have fun. I'm going to go and go through and this time save the notes on all the MCs in case anyone forgets, like, happened yesterday.
Like on the scheduler micro conference.
No,
You
Daniel,
say
we
this.
don't accept that publicly.
That happens. That happens. So bye-bye. I'm really tired.
Bye-bye.